What would happen if the moon were twice its current size? When we look at the moon on a clear night, it's hard to imagine how this seemingly calm and silent object exerts so much influence over Earth. Its phases mark time, its tides shape life in the oceans, and its presence ensures planetary stability on scales we rarely perceive. Now imagine if that silver disk were twice as large in the sky. The impact wouldn't just be in the breathtaking view, but in every detail of Earth's functioning. To understand this hypothesis, we need to go back to the moon's birth. The most accepted theory states that about 4.5 billion years ago, a Mars-sized body called Theia collided with young Earth. From that impact, fragments merged and gave birth to our satellite. If Theia had been larger, or if more material had remained in orbit, the resulting moon could have been twice its current size. Thus, this enlarged version wouldn't be impossible within the cosmic history of our solar system. Doubling the diameter means increasing volume by 8 times. This would make the moon a body with 8 times the mass we know, and that's where the fundamental change begins: gravity. A more massive moon would exert much more intense attraction on Earth, influencing tides, climate, rotation, and even the planet's interior. The question, therefore, isn't just how would it look, but how would we survive in such a world? The first visible sign would be in the oceans. Today, tidal movement is relatively gentle, resulting from the balance between lunar attraction and Earth's resistance. But with a larger moon, this ebb and flow would transform into colossal waves. These wouldn't be isolated tsunamis, but daily tides capable of advancing miles inland. Coastal cities couldn't exist, and beaches would cease to be permanent landscapes, submerged and exposed in endless cycles. This effect wouldn't be limited to ocean shores. Major rivers would be forced to change their behavior. The Mississippi River, for example, could have reversed flows at certain times of day, with waters running against their own current. This process would alter nutrient distribution, soil fertility, and riverside ecosystems. The simple notion of coastline, so important to human life and biodiversity, would become unstable and unpredictable. With oceans in constant turmoil, the atmosphere would also react. Heat transfer from water to air would be much greater, fueling more frequent and intense storms. Hurricanes would emerge in greater numbers, rapidly gaining strength from turbulent seas. The planet's climate would become much more chaotic, less predictable, and more hostile. What we now call climate anomalies could be daily routine in a world dominated by a gigantic moon. These would be the first visible signs, but the greatest transformation would come from the effect on Earth's rotation. Today, the moon functions as a discrete break, lengthening our days by fractions of seconds each century. With 8 times the mass, this deceleration would be much faster. Over millions of years, days would no longer be 24 hours and could reach 40 or 50 hours in duration. The entire planet would spin at a slower rhythm. This lengthening would profoundly affect life. Plants, accustomed to short cycles of light and darkness, would need to change how they store energy. Some might thrive with long periods of light, but many couldn't endure prolonged nights. Diurnal and nocturnal animals would face similar dilemmas, forced to adapt to endless days and excessive nights. Evolution would follow different paths, shaped by the new cadence imposed by the moon. Meanwhile, another essential aspect of the planet would also be transformed: Earth's axial tilt. It's thanks to this tilt that we have seasons, with regular summers and winters. Today, the Moon maintains this axis stable at 23.5 degrees, preventing abrupt oscillations. A larger Moon would make this stability even more rigid, freezing the inclination in an almost fixed position. The result would be a planet of weak and little varied seasons. At first glance, this might seem advantageous because it would reduce climate extremes, but the absence of variation would harm ecosystems that depend on seasonal alternations. Many agricultural crops exist because plants react to cold, drought, or heat. On an Earth with constant climate, agriculture would have to be reinvented. Additionally, polar regions could accumulate ice almost permanently, increasing ice caps and altering sea levels on different scales than current ones. While the planet underwent these changes, the Moon itself would be a very different body from what we see. Its greater gravity would make it more compact, flattening mountains and smoothing craters. Moreover, it would have retained heat much longer, maintaining active volcanoes for billions of years. Instead of a silent satellite, we could observe eruptions and lava flows from Earth. The night sky wouldn't just be illuminated, but dynamic. This extra weight wouldn't be restricted to the satellite. The greater gravitational force would exert intense stress on Earth's crust. Tectonic plates would move more frequently, causing constant earthquakes and volcanic eruptions. Already active regions, like the Pacific Ring of Fire, would live under permanent risk. Earth would become a geologically more turbulent planet, where mountains and volcanoes would rise and disappear on much shorter timescales. Another inevitable effect would be on lunar orbit. Today, the Moon slowly moves away from Earth, about 1.5 inches per year, because it receives energy from the planet's rotation. A more massive Moon would accelerate this process, moving away more rapidly. This would reduce tidal intensity over billions of years, but would also further prolong Earth's days. The balance between the two bodies would continue changing continuously, in an endless cycle. Meanwhile, the night sky would be transformed. A Moon twice as large would reflect much more sunlight, illuminating the night like an immense natural spotlight. The dark sky that today allows us to observe the Milky Way and thousands of stars would be obscured. Many constellations simply wouldn't be visible. Our view of the cosmos would be reduced, and the Moon would reign alone as the dominant figure. More nighttime light would mean less darkness for ecosystems dependent on shadow. Nocturnal predators and prey would need to change behavior, and plants that use absence of light as a signal for certain cycles would be affected. Small changes would add up to great transformations, showing that nothing would escape the reach of a larger Moon. Additionally, its amplified gravity would alter how Earth interacts with space debris. The Moon already functions as a shield, attracting meteors and partially protecting the planet. A larger Moon would capture even more fragments, reducing direct collisions with Earth. On the other hand, it could redirect small bodies into dangerous trajectories, increasing meteor frequency in Earth's atmosphere. It would be mixed protection, more defense, but also more localized risks. With so many chain effects, Earth under the dominion of a larger Moon would be a planet of contrasts. At the same time, this giant Moon would show how much life on Earth is the result of delicate balance. If the impact that formed it had had a different result, we might not be here. A larger Moon could have generated conditions so extreme that complex life never would have developed. In another version of reality, the planet could be inhabited by very different life forms, or by none at all. Thinking about this scenario makes us realize how even details that seem trivial are in fact decisive. The Moon we know, in its current size, allows balanced tides, relatively stable days, and defined seasons. It's silent, but essential. A Moon twice as large would transform all of this into a much more chaotic reality. There are planets where molten iron reigns. When we think of rain, the most common image is water falling in drops, feeding rivers and forests. It's such an everyday phenomenon on Earth that we rarely stop to reflect on how it would be in other worlds. But on some distant planets, clouds don't carry water, but metallic vapors that condense into incandescent drops. This seemingly impossible scenario has already been identified on exoplanets like WASP-76b, located more than 600 light-years from Earth. This is an extremely hot gas giant, very close to its star. The proximity is such that its atmospheric temperature exceeds 4,300 degrees Fahrenheit. Under these conditions, metals like iron don't remain solid, but vaporize and circulate as incandescent clouds in the atmosphere. Just like on Earth, these vapors rise, cool, and condense, but instead of water droplets, what forms are drops of liquid iron. When gravity pulls them down, they fall in metallic rains, melting everything in their path. It's a meteorological process similar to ours, but transported to an almost unimaginable extreme, where each drop is a sphere of incandescent metal. This planet, like many others in its category, is called an ultra-hot Jupiter. Its orbit is so close to its star that a year lasts little more than 1 or 2 Earth days. Additionally, it's probably tidally locked. One side always faces the star, receiving extreme heat, while the other remains in almost permanent darkness. It's this division that creates perfect conditions for metallic storms. On the day side, iron evaporates, mixing with the atmosphere in gas form. Violent wind currents, thousands of times stronger than Earth's, push these incandescent clouds to the night side, and there, in relative darkness, temperature drops enough for iron to condense again. The result is metallic rain, falling in torrents we could never witness up close without being instantly destroyed. On Earth, a storm can last hours and cover hundreds of miles. On WASP-76b, these metallic storms extend for thousands of miles, accompanied by supersonic winds. The sky would be a surreal spectacle, plasma lightning crossing golden clouds and iron drops glowing like embers falling toward a flaming horizon. It's a scene that mixes beauty and destruction in cosmic proportions. The very idea of walking on such a planet is impossible. Any solid object would melt instantly. Spacecraft, probes, or spacesuits wouldn't resist either the day-side's temperature or contact with iron rain. The only way to observe is from a distance, capturing light signals that escape from that violent atmosphere. These are worlds we can imagine but never visit directly with current technology. Each chemical element leaves a unique signature, and in WASP-76b's case, the presence of ionized iron is clear. This is how scientists realized the planet was breathing iron, absorbing it on one side and pouring it out on the other as incandescent rain. This type of discovery shows how the same physical processes we know, evaporation, condensation, precipitation, can take radically different forms in other environments. The physics is the same, but extreme conditions generate results that seem straight out of science fiction. It's interesting to think that these planets help us understand chemistry in states that don't exist on Earth. Iron, which here forms solid structures and supports our buildings, there constantly changes state in a process that mixes geology and meteorology on a planetary scale. Moreover, the existence of planets with iron rain expands our understanding of world diversity. Until a few decades ago, we believed planets were more or less like those in our solar system. But exoplanet discovery showed that extreme environments exist in all directions. There are lava worlds, ice worlds, and as in this case, worlds of liquid metal falling from the sky. Another fascinating point is thinking about these worlds' fate. Over time, stellar wind and proximity to the star can strip away part of the atmosphere, dispersing iron into space. This means these planets not only live in extremes, but also age differently from Earth. Their future is one of constant erosion until they become inert shells under their star's relentless heat. These discoveries also reinforce the importance of modern astronomy. It's only through sophisticated telescopes capable of deciphering starlight that we can imagine such distant phenomena. The fact that we can detect iron rain hundreds of light years away shows how much our technology has already expanded our cosmic vision. A day on Titan can reveal entire lakes of liquid methane. Among all moons in the solar system, few capture as much scientific interest as Titan, Saturn's largest moon. Seen from afar, it appears as just another yellowish point lost in the giant planet's shadows. But beneath its thick, hazy atmosphere hides an intriguing world that bears surprising similarities to primitive Earth. It's the only known place beyond our planet where stable seas and lakes exist on the surface. The difference is that instead of water, these lakes are filled with liquid methane. Titan is so large it rivals planets like Mercury in size. Its diameter of more than 3,100 miles and significant gravity allow retention of a dense atmosphere, something rare in moons. This atmosphere is composed mainly of nitrogen, like Earth's, but with a significant amount of methane and other hydrocarbons. This detail changes everything. Methane, which exists as natural gas on Earth, finds conditions on Titan to behave as liquid, forming rivers, lakes, and even entire seas. Titan's atmosphere is also a protective mantle that hides the surface from direct observation. Viewed through telescopes, its appearance is hazy, as if always covered by orange clouds. It took sending probes to reveal its true face. The Cassini-Huygens mission by NASA and ESA was responsible for opening this curtain of mystery. In 2005, the Huygens module landed on Titan and transmitted the first images of its soil, confirming the existence of channels and structures carved by liquids flowing on the surface. Temperatures on Titan are extremely low, around -290 degrees Fahrenheit. This means water, if present, would be frozen as rock. But methane and ethane under such conditions remain liquid, occupying the role water plays on Earth. This difference creates an atmospheric cycle similar to ours, but based on hydrocarbons, evaporation, condensation, and precipitation, culminating in methane rains that feed lakes and rivers. The presence of these lakes was confirmed in more detail thanks to Cassini's radar. Since dense haze blocks visible light, radar instruments managed to map surface relief. What was revealed was surprising: vast areas covered by liquid bodies, some hundreds of miles across. The largest, called Kraken Mare, has dimensions comparable to the Great Lakes. In a day of observation on Titan, these seas appear on radar as methane mirrors, reflecting the strangeness of an alien world. In Titan's northern hemisphere, the largest liquid reserves concentrate. Kraken Mare, Ligeia Mare, and Punga Mare are examples of seas with depths estimated in hundreds of meters. Cassini detected wave signals on their surfaces, indicating these seas aren't stagnant but dynamic. Cold wind movement blows over methane, forming ripples similar to those we see in terrestrial seas. It's a glimpse of familiarity amid strangeness. These seas aren't just passive liquid collections. They participate in an active cycle that resembles, in many aspects, Earth's water cycle. Methane evaporates under distant sunlight, forms clouds in the atmosphere, and returns to the ground as rain. Methane storms have been recorded, altering the surface and creating new channels. The process sculpts valleys and river networks, suggesting Titan's surface is constantly transforming. The Cassini mission also revealed regions where smaller lakes cluster in interesting patterns. Some appear connected by channels, while others occupy isolated depressions. Lake density varies, and some may contain not just methane, but also mixtures of ethane and dissolved nitrogen. This type of composition makes lakes unique environments, different from anything we know. Still, the principle is the same: liquids flowing, accumulating, reflecting the sky. Titan's climate accompanies these transformations. At certain times, more intense methane rains are believed to fall, replenishing lakes and rivers. This seasonal cycle resembles Earth's, but on a much slower scale, since a year on Saturn lasts almost 30 Earth years. Thus, a summer on Titan can last many years, progressively changing the surface liquid landscape. Lakes also reflect the satellite's long-term dynamics. Models suggest that over time, part of atmospheric methane should disappear, broken by solar radiation into more complex compounds. But since large reserves still exist, scientists believe there's an underground mechanism that replenishes methane. Possibly it's released by cryovolcanoes, volcanoes that, instead of magma, expel frozen water and gases. This would keep the cycle active, ensuring stable lakes for millions of years. Detailed studies indicate some smaller lakes present steep edges, as if they were craters filled with liquid. These formations may result from ground collapses, created when underground methane escapes and leaves cavities. This process resembles sinkhole formation on Earth, but in a completely different environment. Each lake, therefore, is a window into Titan's geological and atmospheric processes. Scientific interest in Titan isn't limited to geology. There's also fascination with astrobiological potential. Although temperatures are extremely low and chemistry involves hydrocarbons instead of water, some researchers believe exotic life forms could exist in these environments. These would be organisms adapted to a non-aqueous solvent, with biochemistry different from ours. There's no confirmation, but the hypothesis makes lake study even more stimulating. Another important point is that these lakes represent significant energy reserves. Methane is common fuel on Earth, and on Titan it's available in immense quantities. Although practical exploitation is far beyond our current capabilities, imagining these lakes as energy oceans is inevitable. They transform Titan into a kind of natural warehouse of cosmic resources. Liquid methane density also brings additional curiosities. It's less dense than water, but dense enough to allow objects to float. Experiments suggest spacecraft could navigate these alien seas like boats, studying their composition up close. NASA even planned a mission called Titan Mare Explorer, a robot boat designed to float on Crane Mare, although the idea hasn't yet left the drawing board. Topography around the seas also reveals fascinating clues. In some regions there are mountain ranges that seem to limit lakes, as if they were natural shores. In others, extensive plains allow methane to accumulate in large depressions. This shows Titan's geography is diverse and complex, shaped by processes that resemble terrestrial hydrology, but in a scenario dominated by extreme cold and hydrocarbon chemistry. Winds on Titan also play a crucial role. Although slower than supersonic winds of gas planets, they're sufficient to move lake surfaces. Waves have been detected, suggesting that at certain moments these liquid masses gain their own life. In a day of prolonged observation, it would be possible to see a lake's surface trembling under cold winds, reflecting weak light filtered through the hazy atmosphere. The thick atmosphere adds another unique effect: light refraction. At certain angles, lakes can shine like golden mirrors reflecting the orange sky. This landscape resembles deserts full of mirages, but here mirages are real. For a probe or astronaut, walking near these lakes would be like exploring a world covered by constant mist, with metallic reflections unexpectedly appearing on the horizon. These lakes' stability in such a hostile environment is a reminder of universal physics resilience. Where there's adequate pressure and temperature, liquids find a way to exist. On Titan, colossal distance from the sun and extreme cold didn't prevent sea formation. They simply exchanged water for methane, creating a cycle parallel to what sustains Earth. The result is a miniature planet with its own oceans, rivers, and rains. For all this, Titan is considered one of the most promising locations for future explorations. Missions like Dragonfly, planned for coming decades, should fly over its surface searching for answers about its chemistry, geology, and perhaps even signs of life. Each mapped lake represents a clue to understanding how different worlds can create systems similar to ours, even without sharing the same basic ingredients. These discoveries show the solar system isn't composed only of solid planets and icy moons. There's enough diversity to generate alien oceans, different meteorological cycles, and liquid surfaces that rival ours in beauty and complexity. And in the simple day of observation on Titan, methane lakes emerge as silent witnesses to a cosmic process that challenges our imagination. Jupiter is so massive it influences even distant planets' orbits. When we observe Jupiter through a telescope, we see only a striped sphere, covered by colorful storms and the famous Great Red Spot. But what the eye doesn't reveal is the dimension of this planet's gravitational power. Jupiter isn't just the largest in the solar system, it's a giant with such immense mass that it shapes the dance of other planets around it. Not by chance, astronomers frequently refer to it as a kind of second sun in terms of influence. The comparison isn't exaggerated. Jupiter is more than 300 times more massive than Earth and contains more than double the mass of all other solar system planets combined. If it were slightly larger, it could even have become a failed star, a brown dwarf. This tremendous size means its gravity extends far beyond its orbit, reaching regions from the asteroid belt to the trajectories of outer planets like Saturn, Uranus, and Neptune. To understand this influence, just remember that Jupiter is more than 400 million miles from the Sun, but still manages to alter orbits at distances several times greater. Its gravity functions as an invisible conductor, keeping asteroids, comets, and even planets in trajectories that, without it, would be very different. The solar system isn't just organized by the Sun's presence. Jupiter plays a silent but fundamental role in this balance. One of the most known examples of its influence is the asteroid belt between Mars and Jupiter. Without the giant's presence, this belt probably would have united to form another planet. But Jupiter's gravity is so intense, it prevents material aggregation. Instead of a solid world, we have a region full of fragments that never manage to unite. In this sense, Jupiter not only shapes planets, but also defines where they cannot exist. Its influence goes beyond the asteroid belt. The so-called Trojan asteroids are rock blocks that share Jupiter's orbit, positioned at gravitational equilibrium points, known as Lagrange points. These asteroids travel as faithful companions of the planet, some ahead, others behind, protected by the giant's gravity. There are thousands of objects trapped in this arrangement, forming a kind of cosmic court that accompanies Jupiter in its orbit around the Sun. Another impressive effect is its interaction with long-period comets. Many of these bodies, coming from the solar system's most distant regions, are deflected or captured by Jupiter. Some are thrown into the solar system, crossing inner planets' orbits, while others are hurled outward in totally different directions. Jupiter acts as a cosmic gatekeeper, controlling who can approach the solar system's heart. This role became evident in 1994 when comet Shoemaker-Levy 9 collided with Jupiter. The planet not only captured the comet, but fragmented it into pieces that fell into its atmosphere like cosmic projectiles. The visible scars from this collision were larger than Earth itself. The event dramatically showed that Jupiter's gravity is a natural barrier against impacts that could hit our planet. But its force isn't limited to smaller bodies. Even planets' own orbits are influenced by it. Simulations show that if Jupiter didn't exist, Mars's orbit would be much more unstable, possibly making development of adequate conditions for life unfeasible. Saturn, Uranus, and Neptune also feel this constant presence, adjusting their trajectories in response to the giant. Jupiter is, in many aspects, the guardian of solar system orbital balance. Jupiter's gravitational effect can be described as a cosmic tide. It exerts small drag forces on more distant planets, gradually altering their orbits over millions of years. These changes are too subtle to be noticed in a human lifetime, but on geological scales they accumulate, slowly redrawing the solar system map. Without Jupiter, planetary choreography would be chaotic. This power also helped shape Earth itself. Many models suggest that in the early solar system, Jupiter migrated from its original position, disturbing the planetesimal belt and launching part of them toward the region where Earth was forming. This bombardment may have been crucial for bringing water and volatile elements to our planet, essential ingredients for life. In this sense, Jupiter not only influences orbits, but perhaps influenced the emergence of the biosphere itself. Jupiter's presence also relates to so-called orbital resonances. These are regions where small bodies enter harmony with the planet's movement, completing their orbits in specific fractions of Jupiter's orbit. These resonances create patterns of stability and instability. In the asteroid belt, for example, there are gaps known as Kirkwood gaps, nearly empty regions, because objects there were expelled by resonance with Jupiter. In Pluto and other Kuiper belt objects, this influence can still be felt. Although Neptune is the closest planet to these bodies, Jupiter's gravity participates in the collective arrangement that maintains their orbits. It's a reminder that its force extends far beyond its immediate neighborhood, interfering even in the solar system's outskirts. Science also suggests that without Jupiter, Earth would have faced many more catastrophic collisions throughout its history. By deflecting comets and asteroids, Jupiter reduced the frequency of impacts capable of sterilizing the planet's surface. This cosmic shield may have been decisive in allowing biological evolution's continuity. That's why in many planetary formation simulations, the presence of a giant like Jupiter is seen as a favorable condition for life's emergence. And it's not just about protection. Jupiter also creates challenges. By launching smaller bodies toward the inner solar system, it temporarily increases collision risk. Earth's history includes periods of intense bombardment, like the so-called late heavy bombardment, more than 3.8 billion years ago, which may have been triggered by Jupiter and Saturn's migration. The same planet that protects can, under certain conditions, also be responsible for catastrophes. Its gravitational influence is so remarkable that astronomers use Jupiter as reference in models of planetary systems outside ours. Many discovered exoplanets are hot Jupiters or cold Jupiters, gas giants that play similar roles in their systems. Understanding Jupiter's gravity is understanding how a giant planet's presence can decide neighboring worlds' orbital fate anywhere in the galaxy. Even other planets' rings and moons carry indirect signs of Jupiter. Its gravitational interactions during solar system formation help define where satellites could exist and where they would be stripped away. In a sense, the gas giant not only controls the present, but also wrote part of the primitive history that shaped surrounding worlds. This massiveness also affects its own composition. Jupiter doesn't have a solid surface. It's composed mainly of hydrogen and helium, the same elements as the Sun. Enormous pressure in its interior creates unique conditions like metallic hydrogen, an exotic state of matter that conducts electricity. This characteristic feeds its magnetic field, the most powerful among solar system planets, further expanding its dominion over surrounding space. Jupiter's magnetic field is so intense, it creates extremely dangerous radiation belts capable of frying spacecraft electronics. It extends millions of miles, influencing even its moon's orbits. Thus, it's not just gravity that makes Jupiter dominant, but also its electromagnetic force, which adds another layer to its role as solar system lord. This set of forces makes Jupiter a planet whose influence is disproportional even on cosmic scales. It's not just an isolated body spinning around the Sun, but a pillar of stability that sustains the entire system's balance. Without it, it's hard to imagine the solar system would have the same organization we know today. There are exoplanets made almost entirely of crystallized carbon. Among modern astronomy's most intriguing discoveries are worlds that seem to defy our notion of what a planet can be. When we think of planets, we tend to imagine familiar scenarios: rocky surfaces, gaseous atmospheres, frozen seas, or erupting volcanoes. But around some distant stars, scientists have found evidence of something completely different: exoplanets made largely of crystallized carbon, which under extreme conditions can take the form of diamond. The idea may sound too fantastic, almost like science fiction, but it's grounded in chemistry. A planet's composition depends on raw materials available in the disk around the star where it formed. If this disk has carbon abundance, instead of oxygen and silicon as in Earth's case, the resulting chemistry will be different. Instead of oceans and continents like ours, these planets can crystallize into vast blocks of hardened carbon, pressed until they become diamonds on a planetary scale. One of the most famous examples is exoplanet 55 Cancri e, located about 40 light-years from Earth. Discovered in 2004, it quickly drew attention for being very close to its star, orbiting it in less than 18 hours. This proximity generates extremely high surface temperatures, sufficient to vaporize rocks. But the most impressive detail came when astronomers analyzed its star's chemical composition and noticed it has unusual carbon abundance. Based on this, the hypothesis emerged that 55 Cancri e could be a diamond planet. Instead of a crust similar to Earth's, with silicates and iron predominating, it could have vast layers of crystallized carbon, hardened under unimaginable pressures. Imagine an entire planet the size of 2 Earths, whose internal structure isn't dominated by granite or basalt, but by diamond in colossal proportions. This concept transformed how we think about planetary diversity. If Earth is a world of silicon and oxygen, and gas giants are made of hydrogen and helium, these carbon worlds add an entirely new category. And it's not just a chemical detail. This changes everything about their geology, atmosphere, and even the heat they retain and release. Such a planet's very brightness would be different from what we see in worlds like ours. A diamond planet's surface would be extremely different. If it were solid and accessible, there would be no blue oceans or green continents, but dark graphite deserts, interspersed with areas of crystalline brilliance. Where pressure was even greater, diamond would form massive blocks, like entire mountain ranges composed of transparent crystals. The landscape, though beautiful in theory, would be completely hostile, marked by extreme temperatures and absence of liquid water. It's important to remember, however, that diamond planet is a simplification. What's imagined is a mixture of different carbon forms: graphite, diamond, silicon carbide, and other compounds. Under intense heat and pressure, these forms interlace, creating a radically different chemical world. But for comparison purposes, calling it a diamond planet helps convey the impact, the idea of a celestial body built in its essence by crystallized carbon. Studies of 55 Cancri e showed yet another fascinating detail. Being so close to its star, it's probably tidally locked, with one side permanently facing the heat and another facing darkness. This creates a brutal contrast between hemispheres: one superheated side covered by magma seas and another side where temperatures plummet. This scenario would make any form of life as we know it impossible, but would create a unique planetary landscape. The day side could be a carbon liquid furnace where constant heat keeps minerals melted in viscous state. The night side could preserve more stable crystallized formations, with temperatures that would allow maintenance of rigid structures. The transition between these two hemispheres, called the terminator line, would perhaps be the most fascinating place, a narrow strip of unstable equilibrium, where heat and cold collide in mineral storms. These contrasts show us how carbon planets aren't just exotic versions of Earth, but completely different entities. Carbon chemistry favors strong and versatile bonds, but also extreme environments when combined with high temperatures. Unlike Earth, where the water cycle shapes rivers and seas, in carbon worlds what flows are molten minerals, and what crystallizes are precious stones on an unimaginable scale. Scientists don't limit themselves to 55 Cancri E. Models suggest that in systems with carbon-rich stars, other similar planets may exist in large numbers. This means diamond worlds may not be rarities, but an entire class of exoplanets still little explored. Each discovery expands the notion that the universe manufactures planets with as much diversity as it manufactures stars. From a geological standpoint, these planets would have very different internal dynamics. Carbon conducts heat differently from silicon, and this could generate unexpected convection patterns in the planetary interior. Carbon volcanoes could expel unusual gases and minerals, altering the atmosphere and even the planet's visible brightness. Instead of ash and lava like on Earth, these eruptions could launch black graphite particles or carbon-rich gases into space. The atmospheric impact would also be striking. The combination of extreme heat and carbon abundance could form dense atmospheres of carbon monoxide and dioxide, perhaps mixed with simple hydrocarbons. These gaseous layers would absorb and reflect stellar light in different ways, creating planets with unique spectral brightness. It's this way, through light signature, that scientists can suspect the existence of such compositions. If it were possible to walk on such a planet, the experience would be unimaginable. The ground could be a mixture of dark rocks, glowing with crystals under starlight. The atmosphere would be thick and toxic, the heat suffocating. But the sight of diamond mountain ranges and bubbling magma seas would create a spectacle of alien beauty. It's an environment both fascinating and completely hostile. The existence of diamond planets also raises practical questions. In terms of material value, they would contain riches beyond any human calculation. But exploring such a world is unfeasible. Heat, pressure, and distance conditions make any mining an impossible dream. Still, they remind us that the universe creates abundance on scales that make our sense of wealth something relative. More than that, these worlds teach about natural laws' flexibility. The same physics and chemistry that produces water oceans on Earth can, in other contexts, produce magma seas or diamond surfaces. There's nothing special about our configuration, it's just one of countless possible variations. Carbon planets are proof of this, showing that cosmic diversity goes far beyond our initial imagination. Investigation of these exoplanets also helps understand planetary system formation. By analyzing stars with different chemical compositions, scientists can predict what type of planets should exist around them. This transforms the study into a tool not just of observation, but of prediction. If a star is carbon-rich, there are good chances that diamond planets are orbiting around it. This perspective expands the search for habitable worlds. Although carbon planets are hostile to us, understanding their formation helps distinguish which systems can harbor planets more similar to Earth. By mapping diversity, we refine our search. Each discovered diamond planet is simultaneously a wonder and a clue. Life may be elsewhere, but cosmic geology doesn't follow our unique model. Finally, reflecting on these worlds is also recognizing our position in the universe. If Earth were rich in carbon instead of oxygen, we wouldn't be who we are. The planet would have evolved completely differently, perhaps without oceans, perhaps without an atmosphere as we know it. Life, if it emerged, would have followed alien paths, shaped by chemistry and extreme environments. Thus, diamond planets aren't just distant curiosities. They're reminders that the universe doesn't repeat itself. It creates infinite variations, each exploring a chemical and physical possibility. The existence of entire worlds made of crystallized carbon shows that reality can be as surprising as the myths we've already invented about it. Black holes slowly evaporate over trillions of years through Hawking radiation. Black holes have always been described as entities of absolute power, regions of space where nothing escapes, not even light. The images of an eternal cosmic devourer, trapping everything that crosses its event horizon. For a long time, they were believed to be, in fact, immortal, but a surprising discovery showed that even these space monsters are doomed to disappear. Quantum physics revealed that slowly, black holes evaporate, releasing their energy drop by drop over trillions of years. To understand this idea, we need to go back to the 1970s when Stephen Hawking combined concepts from relativity and quantum mechanics. Until then, black holes were considered absolutely black objects, incapable of emitting any type of radiation. But Hawking showed that, near the event horizon, quantum vacuum isn't silent. Virtual particles appear and disappear all the time, like sparks in nothingness. This vacuum behavior is essential. Under normal circumstances, virtual particles form in pairs, a particle and its antiparticle, and quickly annihilate. But at a black hole's edge, gravity is so intense it can separate the pair. One particle is captured by the hole, while the other escapes. To a distant observer, this escape equals subtle radiation being emitted by the black hole itself. This process, which became known as Hawking radiation, completely changes our view of these objects, because by emitting radiation, the black hole loses energy. And since energy and mass are equivalent, this means it gradually loses mass too. This loss is extremely slow, but inevitable. Over time, even the largest black holes would end up evaporating. The time scale is what makes this phenomenon so hard to imagine. Stellar mass black holes, formed by star collapse, would take something like 10 to the power of 66 years to completely evaporate. Supermassive black holes, which inhabit galaxy centers, can last up to 10 to the power of 100 years. These are numbers so large they surpass any reference, compared to a current universe that's only 1.38 times 10 to the power of 10 years old. However, this slowness doesn't diminish the process's importance. On the contrary, it connects black holes to the cosmos' final destiny. In a future era when stars no longer exist and galaxies fade, black holes will be the last large-scale remnants. They will dominate the dark universe until they begin evaporating, gradually releasing their energy and disappearing. During most of their life, Hawking radiation is imperceptible. Energy loss is so minimal it doesn't affect their gravitational veracity. But as the black hole becomes smaller, the process accelerates. Approaching the end, it releases increasingly larger amounts of energy in a short period. This climax is marked by a final explosion, where all remaining mass converts to radiation in fractions of seconds. The idea that black holes can die seems contradictory to their nature. After all, they form precisely when gravity overcomes all other forces, collapsing matter to a point of no return. But quantum physics adds a subtle detail. Even where gravity is dominant, vacuum's microscopic agitation cannot be ignored. It's this invisible dance of particles that ultimately slowly undermines the black hole's strength. This phenomenon also reminds us how modern physics is still a construction seeking unity. Hawking radiation could only be predicted by uniting two apparently incompatible pillars: general relativity, which describes the universe on large scales, and quantum mechanics, which governs the microscopic world. Black holes became therefore theoretical laboratories for thinking about these theories' unification. There's still an intriguing aspect: information's destiny. When something falls into a black hole, what happens to the information that described this object? If the black hole eventually evaporates, where does this information go? This is the famous information paradox, one of modern physics' greatest enigmas. Hawking radiation seems not to carry traces of what was absorbed, and this challenges quantum mechanics' fundamental principles. Beyond theory, there are also attempts to imagine how we could detect Hawking radiation. For large black holes, emission is practically impossible to measure, so weak it gets lost in space noise. But for hypothetical very small black holes, like those that could have formed right after the Big Bang, radiation would be intense, possibly observed as high-energy flashes. Finding signals of these events would help confirm the theory. Even without direct observation, the logic behind Hawking radiation is accepted by most physicists. It's based on solid quantum physics principles and has consequences that fit the universe's long-term vision. On unimaginable timescales, the idea that black holes slowly disappear creates a portrait of the cosmos in constant change, without eternal entities. Curiously, evaporation rate depends on size. The larger the black hole, the slower it loses energy. The smaller, the faster. This means the process accelerates as it approaches the end, in a cycle that culminates in a brief and intense explosion. It's like a candle that burns slowly for eras, but ends in a sudden flame before going out forever. This destiny places black holes at the center of discussions about the cosmos's future. In an era so distant, it defies any imagination. Black hole death will mark the end of all astronomical structures. Stars, planets, and galaxies will have disappeared much earlier. Only the slow evaporation of these invisible giants will remain, until space itself becomes empty. So with this thought, we have the image of a cold and dark universe, punctuated by black holes that, one by one, dissolve into radiation. Each final explosion will illuminate for an instant the silent vastness until the last black hole goes out. After that, only an ocean of dispersed particles and energy will remain, without structures, without light, just the echo of processes that took trillions of years to complete. This is Hawking radiation's power, transforming the idea of eternity into finitude, even for the cosmos's most extreme objects. It reminds us that nothing escapes time's wear, not even entities whose very definition seemed to be no return. Physics, with its universal laws, acts on all scales, from the smallest particles to the largest gravitational colossi. For scientists, this process is also a window into broader theories. Understanding how Hawking radiation really works may be the key to uniting general relativity and quantum mechanics in a unified theory of quantum gravity. Until then, each model, each simulation, each calculation is an attempt to bring the invisible closer to human understanding. And although it's unlikely we can witness a black hole evaporating in real time, thinking about this process puts us before cosmic time's immensity. We who measure life in decades are talking about phenomena that unfold over trillions of years. It's almost impossible to imagine, but it's precisely this contrast that gives the idea its fascination. Hawking radiation also forces us to rethink what it means to exist in the universe. If even a black hole, symbol of permanence and absolute imprisonment, can disappear, then nothing is truly eternal. The entire cosmos is a flow, where each structure has beginning, middle, and end. Most atoms in your body were forged inside stars that exploded. When we think about the human body, we usually associate its composition with simple elements like water, proteins, and minerals. But if we go beyond the surface and look at the atomic scale, we discover a much older and more surprising story. Every carbon atom in our cells, every oxygen atom we breathe, every calcium atom in our bones, originated in distant and violent places in the universe. Most of them were born in stars that lived and died long before Earth's formation. The universe began with only three main elements: hydrogen, helium, and small amounts of lithium. These atoms emerged in the first minutes after the Big Bang, in a process known as primordial nucleosynthesis. They're simple elements that compose the cosmos's foundation, but insufficient to form rocky planets or sustain complex life. Other chemical elements, oxygen, carbon, iron, and many others, only appeared later inside stars. Stars are true nuclear furnaces. In their cores, gravitational pressure is so intense that light atoms are fused into heavier atoms. The process begins with hydrogen fusion into helium, releasing energy that keeps the star shining. But as the star ages and its fuel depletes, more complex reactions take over, creating elements like carbon, oxygen, and even magnesium. All this occurs at temperatures and pressures that cannot be reproduced in any terrestrial laboratory. Stars with mass similar to the Sun can fuse elements up to carbon and oxygen. Much larger stars with dozens of times solar mass take this process much further. In their cores, successive nuclear reactions create elements like silicon, sulfur, calcium, and iron. It's a kind of cosmic ladder where each fusion stage releases energy until reaching iron, a point where the star can no longer extract energy from fusion. At this moment, it becomes unstable. When nuclear fusion reaches this limit, the star's balance collapses. Gravity overcomes internal pressure, and the core implodes in a fraction of a second. The result is a supernova, a colossal explosion that releases more energy than the Sun will emit in its entire lifetime. It's in this instant that even heavier elements like gold, uranium, and lead are formed through rapid neutron capture processes. In a few seconds, a dying star enriches space with new chemical ingredients. These explosions don't just create elements, but also scatter them throughout interstellar space. A supernova's shockwave sweeps surrounding material, launching atoms in all directions at extremely high speeds. This material mixes with gas and dust clouds, enriching them with metals and complex compounds. Space regions previously composed only of hydrogen and helium come to contain oxygen, carbon, iron, and other elements fundamental for planet formation and, eventually, for life. Clouds enriched by generations of stars are the nurseries of new stars and planetary systems. When one of these clouds collapses under its own gravity, a new star forms surrounded by a disk of gas and dust. In this disk, small grains collide and clump together, growing until they become planets. Thus, every rocky planet, including Earth, is made from the remains of ancient stars. Literally, the material composing soil, mountains, and even the water in our oceans was inherited from stellar explosions. The iron present in our blood is a direct example of this heritage. It couldn't have been produced in the universe's early phases, nor in small stars. Only supernova explosions or neutron star collisions can synthesize iron in large quantities. Every hemoglobin molecule that carries oxygen in our cells bears an iron core forged in one of these cosmic catastrophes. Without this element, cellular respiration wouldn't be possible. The calcium in our bones has a similar origin. Created in nuclear reactions inside massive stars, it was launched into space in ancient supernovas. Over billions of years, this calcium incorporated into cosmic dust that formed Earth, and much later into structures that support our bodies. The same applies to carbon, present in all organic molecules, and oxygen, essential for life. Every breath we take is, in a way, direct contact with stellar history. These atoms traveled through cosmic eras before gathering in us. Many were launched into space millions or billions of years before the solar system's formation. They floated in interstellar clouds, participated in new star formation, and were recycled many times. When the Sun was born 4.6 billion years ago, there was already a rich reserve of heavy elements accumulated by previous stellar generations. It was this reservoir that gave rise to Earth and all its inhabitants. Space probe Herschel, among others, helped map interstellar cloud composition and confirm these heavy elements' presence. Each observation reinforces the idea that the universe is a gigantic recycling system. Stars are born, live, die, and spread raw materials for new star and planet formation. This continuous cycle ensures essential elements don't disappear, but are reused in new combinations. Supernovas aren't solely responsible for this enrichment. Collisions between neutron stars, incredibly dense objects formed after supernovas, also play a fundamental role. These collisions produce heavy elements in immense quantities, especially gold and platinum. Recent gravitational wave observations confirmed this type of event is one of the main sources of these elements in the universe. This shows different processes contribute to the chemical complexity we find today. A fascinating aspect is that each galaxy region may have slightly different chemical composition, depending on the history of supernovas and stellar collisions around it. This means in other parts of the Milky Way, planets may have distinct metal quantities or different element combinations. Ultimately, stellar chemical diversity shapes the diversity of worlds born around them. Astronomers use spectroscopy to identify this heritage in distant stars. Light emitted by a star carries lines, indicating which elements are present in its composition. By studying these signatures, it's possible to trace the universe's chemical family tree. This helps understand how different stellar generations contributed to enriching the galaxy over billions of years. Heavy elements' presence on Earth also explains why it's a rocky rather than gaseous planet. Without previous supernova contributions, there wouldn't be enough material to form a solid crust, metallic core, or atmosphere rich in complex compounds. Giant planets like Jupiter are composed mainly of hydrogen and helium, the primordial elements. Earth exists thanks to accumulation of atoms created in much more violent processes. Ages of meteorites studied by scientists confirm this story. Many contain interstellar dust grains older than the solar system itself. These grains are literally fragments of stars that died before the sun's birth. By analyzing them in laboratories, it's possible to identify isotopic signatures, revealing their origin in supernovas or neutron stars. It's like holding in hands a small sample from another time and place in the universe. This heritage can also be seen in our planetary core. Iron composing Earth's center, responsible for generating the magnetic field that protects us from solar radiation, also came from these ancient stars. Without it, Earth's atmosphere probably would have been eroded by solar wind, and the planet wouldn't have maintained conditions for life. Once again, Earth's current functioning depends on events that occurred in much earlier eras. When studying young stars in formation, astronomers observe this process is ongoing. New planetary systems are being born today in clouds enriched by previous generations. This means somewhere in the galaxy, planets are still receiving their load of heavy elements, preparing the stage for life forms that may emerge in the future. The cycle that gave us origin is still active, continuously repeating at different scales. All this shows we're not made just of local matter. We're composed of atoms that have already passed through stellar explosions, interstellar journeys, and mixtures in cosmic clouds. There's nothing special about these elements themselves, but how they were gathered on Earth created unique conditions for life. Every molecule in our body carries the chemical signature of cosmic processes that happened billions of years before us. This chain of facts makes clear that life on Earth only exists because the universe had already produced the necessary ingredients. Without supernovas, there would be no carbon to form organic molecules, no oxygen to breathe, no iron for blood circulation. We're literally the second or third generation of matter, reused and regrouped after violent events on cosmic scales. The speed of light is an insurmountable cosmic limit. Nothing can exceed it. When someone hears that nothing can travel faster than light, the information sounds almost like common sense. But what often goes unnoticed is that beyond being fast, Light is a universal speed standard, a limit that appears throughout modern physics structure. Understanding this requires going beyond the obvious. It's diving into experiments, equations, and consequences that define the very notion of space and time. The first surprise is that light doesn't need a medium to propagate. Sound needs air, ocean waves need water, but light crosses absolute vacuum. This already places it on a special level. For centuries, it was believed there should be some invisible ether carrying its waves. This mystery was only solved in the late 19th century, when experiments showed such ether simply didn't exist. Light was self-sufficient, and its speed remained constant regardless of the observer. This result came from the famous Michelson-Morley experiment in 1887. They built an apparatus to measure differences in light speed in different directions, hoping to capture Earth's movement effect through the supposed ether. But they found no difference at all. It didn't matter if Earth was moving, light always traveled at the same speed, 186,282 miles per second. It was a shocking discovery that opened the path for one of science's most profound revolutions. Einstein, in 1905, took this result and placed it at the center of special relativity theory. If light always has the same speed, then space and time cannot be absolute. They must adjust to maintain this constancy. From this arise effects like time dilation and space contraction. The faster an object moves, the more time slows down for it, and the more its length shortens, all to ensure light remains insurmountable. This idea may seem abstract, but it's been tested countless times. Subatomic particles in accelerators like muons live longer when approaching light speed, exactly as predicted. GPS satellites also need to correct their clocks, taking these relativistic effects into account. If they didn't, navigation systems we use daily would be wrong within minutes. Another point that makes light unique is its relationship with energy. The famous equation E equals mc squared shows that energy and mass are linked by light speed squared. This means the faster we try to accelerate a particle with mass, the more energy is needed. Particle accelerators at CERN have already taken protons to more than 99.9999998% of light speed. But no matter how much energy is provided, they never exceed it. The required energy approaches infinity. It's as if the universe placed an invisible wall. We can approach indefinitely, but never cross it. And this isn't a technological limitation, it's a law of nature. Massless objects like photons are already born traveling at light speed. Mass with objects, however small, can never reach it. This difference divides the universe into two types of travelers, those that always move at maximum speed, and those that can only try to approach it. Light's constancy also defines the causality limit. In other words, nothing can transmit information faster than light. If it were possible, events could reverse, with effects happening before causes. This would create unsolvable paradoxes. Light, therefore, beyond being a physical limit, is also a logical limit. It ensures the universe maintains a coherent sequence of events. A practical example lies in distant stellar explosions. When a supernova occurs thousands of light years away, its light takes all that time to reach us. We see the event long after it happened, but never before. Light dictates cosmic information's rhythm. Everything we know about the distant universe is limited to what light, or other radiation forms like radio waves and gamma rays, manage to bring to us. Another intriguing detail is that light speed is a surprisingly low limit in cosmic terms. The universe is too enormous. Even traveling at maximum permitted speed, it would take us more than 4 years to reach the nearest star, Alpha Centauri. To cross the galaxy would take 100,000 years. This disparity between maximum speed and cosmic distance explains why, so far, interstellar travel belongs to the field of theory and science fiction. Still, science studies ways to circumvent this limit without violating it. One of the best-known ideas is the concept of space warp or warp drive, inspired by science fiction but seriously investigated in physical theories. The idea isn't to exceed light, but to manipulate space-time, compressing it ahead and expanding it behind the ship. This way, it would be space that moves, not the ship. The limit wouldn't be broken, just circumvented. Another proposal is using wormholes, theoretical shortcuts that would connect distant space-time points. They also wouldn't violate light speed because the journey would happen in shortened space. But until today, there's no experimental evidence these shortcuts actually exist in stable conditions. They remain fascinating hypotheses, but distant from any practical application. Meanwhile, scientists continue exploring light limit implications on smaller scales. In laboratories, it's possible to slow light by making it pass through certain materials, like special glasses or ultra-cold atom condensates. In these environments, light can move thousands of times slower. But in vacuum, nothing stops it. This is its natural state, an immutable speed no massive particle can equal. The limit also defines what we call event horizon in black holes. There, gravity is so intense that not even light can escape. It's not that light slows down, it's space-time that curves in such a way that all trajectories lead inward. This creates universe regions from which no information can reach us, reinforcing the idea that light is the maximum frontier between accessible and inaccessible. On cosmological scales, light speed mixes with universe expansion. Distant galaxies aren't fleeing from us faster than light in the traditional sense, but because space itself between us and them is expanding. This detail generates confusion, but the rule remains valid. Locally, nothing crosses space-time faster than light. What changes is that the universe's fabric can stretch, carrying everything it contains. This limit also explains why the visible universe has an edge. We can't see beyond about 46 billion light-years because light from more distant regions simply hasn't had time to reach us since the Big Bang. The cosmos may be much larger, perhaps infinite, but our window is determined by light speed and universe age. It's a natural frontier no telescope can surpass. With this, it's clear that light speed is modern physics's backbone. Appearing in relativity theory, Maxwell's electromagnetic equations, quantum mechanics, and even cosmology. It's the number that stitches together all known reality levels, from infinitely small to infinitely large. And despite seeming abstract, this limit is present in our lives. Without it, GPS wouldn't work, satellites wouldn't be precise, and even the electricity we use would behave differently. The fact that we live in a universe governed by this specific number makes possible an order of phenomena that sustain life and technology. The Milky Way and Andromeda are on a collision course. Imagine looking up at the night sky and knowing that beyond all the stars you see, an entire galaxy is approaching in our direction. This isn't just a simple distant point or small diffuse cloud. It's Andromeda, a colossal galaxy with more than 1 trillion stars, traveling in a straight line to collide with the Milky Way. This encounter is inevitable, already underway, and will be one of the most grandiose cosmic events in our local universe's history. The current distance between the two galaxies may seem reassuring, about 2.5 million light-years. However, on cosmic scales, this isn't much. Both have been trapped in a gravitational dance since they formed, and mutual attraction ensures that, within billions of years, they will meet. It won't be a collision like two solid objects, but rather a slow and spectacular merger where stars, gases, and dust will reorganize into a new structure. This approach's velocity is impressive. Andromeda advances toward the Milky Way at about 68 miles per second. This means every second it approaches at nearly the speed of an interstellar rocket. Despite this, space's immensity makes the process much longer than we can perceive. Billions of years will pass before true impact happens, but we can already measure its trajectory precisely. These measurements are possible thanks to careful observations made with modern telescopes. The Hubble Space Telescope, for example, was crucial for confirming Andromeda's movement toward our galaxy. Small variations in its star's light revealed the speed and direction of this displacement. Combining this data with computer simulations, astronomers could predict not only the collision, but also how it should unfold. When two galaxies meet, it doesn't mean all their stars will directly collide. In fact, distances between individual stars are so great that the chance of two crashing is almost nil. What really happens is their gas and dust clouds interact intensely. These clouds collide, compress, and initiate star formation bursts. Thus, the Milky Way's merger with Andromeda will create an entire generation of new stars. During the process, both galaxies will cease having the spiral shape we know. The beautiful spirals of the Milky Way and Andromeda will be distorted by gravity, forming long star arcs and luminous tails. This cosmic spectacle will be visible from any inhabited point, transforming the night sky into a stage of constant movement. Over millions of years, the two spirals will merge into a larger elliptical galaxy. Astronomers have even given this future merger a name, Milkomeda, a mixture of Milky Way and Andromeda. This new galaxy will be much larger than the two originals, possibly one of the largest in the local group, which gathers dozens of smaller galaxies in our cosmic neighborhood. The merger will be slow, taking billions of years, but the final result will be a single colossal structure shining intensely in the universe. Another important aspect is the central black hole's destiny. Both the Milky Way and Andromeda harbor supermassive black holes in their nuclei. When the galaxies unite, these black holes will also eventually merge. The process should release enormous amounts of energy in the form of gravitational waves, space-time distortions we can already detect with modern instruments like LIGO. Meanwhile, individual stellar systems like our solar system won't be destroyed, but may be displaced to new regions of the galaxy. Simulations suggest the Sun might end up in a more distant orbit from the galactic center, or even be launched outward, becoming part of the new galaxy's halo. This wouldn't destroy the solar system, but would radically change our position in the cosmos. The beauty of this phenomenon is that we already have similar examples in other parts of the universe. Telescopes have recorded images of colliding galaxies, like the antennae galaxies, which show exactly what happens during merger. Long star tails, regions intensely illuminated by new stellar formations, and nuclei being pulled toward each other. These records serve as a preview of what will happen to our galaxy. The timescale, however, is unimaginable in human terms. We're talking about billions of years, periods so long they surpass all of Earth's and life's history. This means no current civilization will witness the collision's climax, but from an astronomical standpoint, it's a relatively close event, since the universe is 13.8 billion years old and we're only a few billion years from the merger. Another intriguing detail is that the collision won't be just between the Milky Way and Andromeda. The smaller galaxy Triangulum, or M33, may also participate in the event. It orbits Andromeda, and depending on gravitational interactions, could collide together or be captured by the new galaxy. The result could be a triple merger, even more complex and spectacular. Despite the grandeur, this process is natural and common in the universe. Galaxies are in constant motion, and mergers are part of their evolution. Many elliptical galaxies we see today formed precisely through these collisions. In a sense, the Milky Way's destiny isn't an exception, but an inevitable stage of its history. The merger will also impact dark matter distribution. Both the Milky Way and Andromeda are enveloped by invisible halos of this mysterious material. When they unite, these halos will also merge, creating a new gravity distribution. This process may provide precious clues about dark matter's nature, one of modern physics' greatest enigmas. In energy terms, the process will be extremely intense, but not on a scale that destroys planets or individual stars. Interstellar gas interaction, on the other hand, will create shock waves that illuminate vast regions. The night sky would be dotted with new bright points, each representing a newly born star. For any future observer, it would be like living in a galaxy on fire, in constant renewal. Understanding this phenomenon also depends on computer simulations. Using supercomputers, astronomers can predict how stars and gases will move during the merger. These simulations show that even amid chaos, order emerges in the end. Spiral galaxies reorganize into a larger, stable structure. It's a cosmic dance that, though chaotic in details, follows gravity's rules in its essence. This type of study helps understand galaxy formation throughout the universe. Many structures we observe in distant telescopes are probably results of similar mergers. By predicting the Milky Way's destiny, astronomers also better understand other galaxies' history, reconstructing cosmic past, and anticipating the local universe's future. The fact that Andromeda is visible to the naked eye on dark nights makes this story even more impactful. When we see that faint blur in the sky, we're looking at an entire galaxy slowly walking in our direction. It's a silent vision, almost imperceptible, but loaded with consequences for the future. What today is just a diffuse point will become, in billions of years, part of the same celestial body we inhabit. There are stars that spin hundreds of times per second, pulsars. An object the size of a city, but with more mass than the entire sun, can spin hundreds of times in just 1 second. It's hard to believe, but these stars exist. They're called pulsars, and each rotation fires beams of radiation that cross space like cosmic lighthouses. When we detect these pulses here on Earth, it seems like we're hearing the heartbeat of a stellar heart on an unimaginable scale. Pulsars are a special type of neutron star, the remnants left behind after massive stars explode in supernovas. During the explosion, most mass is launched into space, but the core collapses under its own gravity. The result is an incredibly compact object, all of a star's mass compressed into a sphere just 12 miles in diameter. This absurd density is the key to their vertiginous rotation. When the core collapses, the star obeys a physical principle called conservation of angular momentum. It's the same effect that makes a figure skater spin faster when pulling in their arms. In a star's case, shrinking from millions of miles to just a few dozen means multiplying rotation speed to extreme levels. The result is pulsars that spin not once, not 10, but hundreds of times every second. The fastest recorded, called PSR J1748-2446 AD, spins 716 times per second. This means in less than a blink of an eye, it has already completed hundreds of rotations. If it were on Earth, the velocity at its surface would be about a quarter of light speed. No known material would resist this, but the star's crushing gravity keeps everything together. What makes pulsars even more fascinating is their magnetic field. They don't just spin fast, but also emit concentrated beams of electromagnetic radiation. These beams exit through magnetic poles, and as the star rotates, sweep space as if they were lighthouse beams rotating in a harbor. Each time this beam crosses Earth, we detect a pulse. That's where the name pulsar comes from, a stellar lighthouse that marks time with incredible precision. This regularity is so stable that for a long time, when the first pulsars were discovered in the 1960s, astronomers wondered if they weren't artificial signals. The pulse cadence was so precise it seemed like a radio transmitter. Today we know it's pure physics, but the precision is so remarkable that pulsars are already used as true cosmic clocks, marking time intervals more stable than any atomic clock on Earth. Different types of pulsars exist. The youngest spin incredibly fast due to initial impulse from collapse. Over time, they lose energy and slow rotation, but some speed up again. This happens when they're in binary systems receiving matter from a companion star. The sucked gas accumulates and transfers energy, re-accelerating the pulsar. These are called millisecond pulsars, precisely because they spin on millisecond scales. A neutron star's density is almost impossible to conceive. A single teaspoon of its material would weigh billions of tons. This density keeps the star intact even under such rapid rotations. Extreme gravity prevents it from disintegrating, even when its surface is moving at speeds that defy any comparison with what we know. Pulsars also function as natural probes for studying space. Their pulses cross the galaxy, and by measuring how these signals reach us, it's possible to infer interstellar medium properties. They help map magnetic fields, gas distributions, and even gravitational waves. Each pulsar is a laboratory in continuous operation, scattered throughout the universe. Another curious detail is that pulsars aren't isolated rarities. It's estimated that in the Milky Way alone, there are tens of thousands of them. Many remain invisible because their radiation beams aren't aligned with Earth. But those we can detect are already sufficient to show that the galaxy pulses with these regular beats, silent echoes of dead stars still spinning furiously. Pulsar study also brought unexpected discoveries. It was from observing one of them that scientists confirmed gravitational waves' existence long before direct detection made by LIGO. Two pulsars in orbit around each other lost energy exactly at the rate predicted by Einstein's relativity theory. It was one of the most elegant proofs that space-time fabric can vibrate. In energy terms, pulsars are impressive natural machines. Each rotation releases colossal amounts of radiation, capable of ionizing surrounding space. In some cases, they create spectacular nebulae, illuminating gas expelled by the supernova that originated them. The most famous is the pulsar in the Crab Nebula's heart, visible even with amateur telescopes. Its constant spin keeps the nebula glowing centuries after the explosion that created it. Pulsars are also clues about massive stars' destiny. By studying their characteristics, astronomers can understand how different stellar masses collapse, which become black holes, and which transform into neutron stars. They are, in a way, living records of one of the universe's most violent processes, a giant star's death. However exotic they may seem, these objects follow physics laws we know. Conservation of angular momentum, electromagnetism, and extreme gravity are principles governing their behavior. This makes pulsars not just astronomical spectacles, but also tools that test our physics understanding. They show how far our theories work and where they begin to be challenged. Study of these objects continues advancing. Modern telescopes, sensitive to different radiation ranges, detect pulsars in radio, X-rays, and even gamma rays. Each range reveals different details: magnetic field, rotation speed, interaction with surroundings. With each discovery, the image of these dead stars becomes more complete, but also more intriguing. The universe may contain wormholes, shortcuts through space-time. The idea that the universe might contain invisible shortcuts has always sparked fascination. In science fiction movies and books, they're portrayed as glowing tunnels connecting distant points in the cosmos within seconds. But the concept of wormholes didn't originate from popular imagination. It emerged from theoretical physics itself, when scientists realized that Einstein's equations, which describe gravity, allowed strange solutions where space and time could fold and connect. These shortcuts receive the name wormholes because they resemble the simple idea of a worm crossing an apple. Instead of going around the entire surface, it burrows through the fruit and reaches the other side faster. In space, the equivalent would be traveling between stars or galaxies without needing to cover the complete distance. The shortcut would be a tunnel, invisible to the eye, but real within general relativity's mathematics. The concept was formally introduced in 1935 by Albert Einstein and Nathan Rosen. They described a solution known as the Einstein-Rosen bridge, which would connect two distinct points in space-time. Although it was only a mathematical construction, it opened the path for decades of theoretical exploration. Since then, scientists have wondered, could such bridges actually exist? And if they exist, would they be stable enough to allow matter passage? To understand this possibility, we must remember that space-time isn't rigid. It can curve under the presence of mass and energy. The gravity we feel is actually the result of this curvature. If this geometry can be distorted to create orbits and event horizons, it could also be distorted to create passages. It's a natural consequence of the equations, though never directly observed. One of the first difficulties is stability. Wormholes, in theory, would tend to collapse rapidly. This means any attempt to cross them would result in almost instantaneous implosion. To keep them open, a form of exotic matter with negative energy would be necessary. This idea goes beyond any known substance, but isn't dismissed by physics. Quantum phenomena suggest energies of this type may exist on small scales. Another question is where these wormholes could arise. Some models suggest they may form naturally in regions of extreme density, like near black holes. Others argue they could exist on microscopic scales at the limits of quantum space. In these cases, they would be invisible and too unstable to be used. Still, the theoretical possibility remains. The universe could be filled with ephemeral tunnels that constantly open and close. In 1988, Kip Thorne and his colleagues took an important step by demonstrating that with exotic matter, it would be possible to construct wormholes. This idea gained popularity because it was used as the basis for fiction works, like the movie Interstellar. In the plot, the tunnel is used to connect two distant galactic points. Although the film is fiction, the physics shown there was based on real calculations, supervised by Thorne. Beyond space travel, there's another intriguing consequence: time travel. Some mathematical solutions indicate that if wormhole endpoints moved at different speeds or were exposed to intense gravitational fields, they could become desynchronized in time. This would open the possibility, at least theoretically, of crossing not just space, but also the past or future. This idea is highly controversial, but is predicted in some general relativity scenarios. However, physics also imposes severe restrictions. Even if a wormhole could be stabilized, it will probably have energy and mass limits. A spacecraft crossing it could trigger fatal instabilities. Additionally, intense radiation would tend to accumulate inside the tunnel, making it dangerous. In other words, the fact that they're possible in equations doesn't mean they're viable in practice. Scientists have sought ways to detect wormholes, should they exist naturally. One possibility would be observing unusual gravitational distortions. Just as black holes bend light around them, a wormhole could leave a characteristic signature. Another method would be looking for anomalies in star or interstellar gas movement, which could be reacting to an invisible tunnel's presence. So far, there's no direct evidence. In cosmology, there's also the idea that the primitive universe itself could have produced wormholes. In the first instance after the Big Bang, when space-time was in a turbulent state, connections could have formed spontaneously. These primordial tunnels, if they still exist, could be scattered throughout the cosmos. Some could be microscopic, others large enough to link distant galaxy regions. Even without direct observations, studying wormholes has scientific value. They test general relativity's limits and show where theory meets quantum mechanics. They're tools for exploring what happens when physics is taken to extreme conditions. If they exist, they could be the key to understanding phenomena that still escape our comprehension, like fundamental force unification. It's important to note that wormholes also have conceptual limitations. Unlike black holes, which have been detected and photographed, they remain only in the hypothesis field. This doesn't mean they are impossible, but that we don't yet have instruments capable of confirming or denying their existence. They are, until now, mathematical solutions awaiting physical evidence. Some alternative models suggest wormholes could be disguised as black holes. To a distant observer, the difference between the two would be minimal since both bend light extremely. Only a more detailed study of matter dynamics around them could reveal whether we're facing a traditional black hole or a cosmic tunnel. This possibility still intrigues researchers. There are also proposals that extremely high-energy particles, like cosmic rays, could interact peculiarly if they crossed a wormhole. Detecting unusual signatures in particle colliders or space observatories could, in the future, be a way to search for indirect evidence. Although still speculative, this research line reinforces the idea that wormholes don't belong only to fiction. Study of these objects also finds limits in mathematical language itself. Einstein's equations describe coherent scenarios, but when applying real conditions like quantum instabilities and radiation, many models collapse. This shows that general relativity alone may not be sufficient to describe wormholes. That's why they're frequently used as theoretical laboratory to test quantum gravity hypotheses. Even though most scientists view wormholes with caution, interest is growing. Every time a telescope like James Webb or gravitational waves observatories make new discoveries, hypotheses arise that this data could hide clues about exotic structures. So far, nothing has been found, but the search continues because each eliminated hypothesis also brings us closer to the truth about how the universe works. In parallel, wormhole study has practical applications in mathematics and computerful physics. Advanced simulations requiring supercomputers help understand how space-time could behave under extreme conditions. Even if we never find a real wormhole, these models offer insights about gravity, energy, and cosmic structure. The idea also helps inspire new generations of scientists. Although this isn't the main focus, the simple fact that equations allow such possibilities shows how physics can be surprising. Instead of a universe limited to predictable trajectories, we have a space-time capable of generating solutions as exotic as cosmic shortcuts. It's a reminder that science is still exploring only the surface of what's possible. What would happen if Earth had no atmosphere? When we look at the blue sky during the day or at stars on a clear night, we rarely think about the invisible role atmosphere plays. It seems just like a blanket of air, but it's much more than that. It regulates climate, enables breathing, protects against radiation, and controls the planet's temperature. Imagining an Earth without atmosphere is imagining a world completely different from the one we live in, a naked planet directly exposed to space. The first impact would be visual. Without atmosphere, the sky wouldn't be blue. The day's blue color results from sunlight scattering by air molecules. Without this effect, the sky would always appear dark, even at high noon, and the sun would stand out as a bright disk against a black background. Stars would remain visible during the day, as happens on the moon. The planet would lose the smooth transition between night and day, replaced by absolute contrast. But aesthetic change would be just the problem's surface. Without atmosphere, Earth would have no air to breathe. This means life as we know it would cease to exist instantly. Animals, plants, and humans wouldn't resist even for a few minutes. Oxygen would disappear, and with it the ability to sustain basic biological processes. The planet would instantly become uninhabitable for any air-dependent life form. Beyond breathing, atmosphere is what maintains pressure at sea level. Today, we live under approximately 1 atmosphere, or 1 bar of pressure, which prevents liquids from boiling at common temperatures. Without this pressure, water from oceans, rivers, and lakes would begin evaporating violently, not because of heat, but due to lack of containment. Large masses of water would pass directly from liquid to vapor state until disappearing into space. This process would be devastating for planetary balance. Entire oceans would transform into vapor clouds, slowly escaping Earth's gravity. Although part of this water could freeze on shadowed surfaces, most would end up lost to space. In little geological time, Earth would transform into an arid world, similar to Mars, marked by deserts and bare rocks. Climate would also cease to exist. Today, atmosphere distributes heat, transports moisture, and creates currents that balance temperatures. Without it, there would be no wind, clouds, or rain. The planet's surface would be divided into extremes. On one side, sun-facing regions would reach temperatures above 212 degrees Fahrenheit. On the other, shadowed areas would drop to -240 degrees Fahrenheit or less. Without a medium that redistributed heat, Earth would become a planet of extreme contrasts. This thermal imbalance would be felt in every detail. Sun-exposed soil would become superheated, while regions in prolonged shadow would freeze. There would be no relief, no smooth transitions. It would be a planet burned on one side and frozen on the other, with no stable zone to harbor life. Only deep caves or the subsurface could offer slightly less fatal conditions. Another immediate effect would be loss of radiation protection. Atmosphere functions as a filter that blocks part of ultraviolet radiation and absorbs harmful rays. Without it, the planet's surface would be directly bombarded by solar and cosmic radiation. This radiation would not only sterilize the surface, but also rapidly degrade any organic molecule, preventing life's formation and maintenance. The ozone layer, which is part of atmosphere, plays an essential role in this blocking. Without it, Earth would be exposed to intense ultraviolet rays, equivalent to thousands of sun-tanning sessions simultaneously. The surface would become naturally radioactive, unable to sustain living organisms. Any attempt at surface life would be unfeasible. Meteors would also become a constant threat. Today, atmosphere functions as a natural shield, burning most space debris before it reaches the ground. Without it, every rock fragment, even the smallest, would hit the surface at full speed. Earth would be under continuous bombardment, marked by craters as we see on the Moon. The surface would be sculpted not by wind or rain, but by endless cosmic impacts. Another fundamental point is that without atmosphere, there would be no sound. Sound needs a material medium to propagate. Without air, environments would be absolutely silent. Explosions, winds, footsteps, no noise would exist. The planet, though visually dynamic in its space exposure, would be a place of absolute silence, as happens in lunar environments. Photosynthesis, the basis of almost all terrestrial life, would also be impossible. Without carbon dioxide in atmosphere, plants would have no way to perform the process that generates energy and oxygen. This reinforces that even before considering temperature extremes or radiation, Earth's ecological foundation wouldn't exist. The planet would rapidly lose any trace of complex life. Atmosphere's absence would also directly impact geological cycles. On current Earth, wind and rain sculpt mountains, valleys, and rivers. Without these agents, atmospheric erosion would cease. Relief would be reshaped only by internal activity, like volcanoes and tectonics, and by meteor impacts. In few eras, the surface would resemble the Moon's, preserved craters, stagnant landscapes, and absence of constant erosion. Without atmosphere, there would also be no heat transport by convection. This means volcanic eruptions and other internal activities would have much more localized effects. Heat wouldn't spread through air, remaining restricted to fissure proximities. These places could temporarily offer some heat, but wouldn't be sufficient to counterbalance the rest of the planet's intense cold. The water cycle, which depends on atmosphere to redistribute vapor and produce rain, would cease to exist. There would be no rivers flowing to seas, no clouds forming in the sky. The hydrosphere, as we know it, would collapse. Eventually, only ice could remain in isolated regions, resembling frozen deposits found on Mars. But the vibrant dynamics of oceans and rains would simply cease being part of Earth. Curiously, continents would also be affected by lack of atmospheric erosion. Today, rocks wear down with wind and water, releasing minerals that feed ecosystems. Without this process, Earth's crust would remain practically unchanged, except when hit by meteors or shaped by volcanoes. Fertile soil would disappear, and the surface would just be bare rock, without nutrients necessary to sustain organisms. Another often forgotten detail is the effect on artificial satellites. Atmosphere, even in its highest layers, exerts friction on objects in low orbit, making them eventually return to Earth. Without atmosphere, this friction wouldn't exist. Space junk and inactive satellites would remain orbiting indefinitely, accumulating around the planet in an increasingly dense debris belt. Atmosphere's absence would change even sunlight perception. Today, sunrise and sunset are marked by smooth transitions, created by light scattering in air. Without this effect, the sun would appear and disappear from the horizon in seconds, without orange colors or transitions. It would be an abrupt light and shadow cycle, reinforcing the sensation of an exposed planet without filters. Long-term, without atmosphere to retain heat, the planet would tend to cool. Over billions of years, Earth could end up frozen, with only areas near active volcanoes maintaining some heat. This scenario would resemble icy moons like Europa, but without protection from a stable outer ice layer. It would be a vulnerable and arid planet, swept by space. The closest comparison to what Earth without atmosphere would be can be found on the Moon. Both bodies would have crater-marked surfaces, extreme temperatures, and absence of constant erosive processes. But Earth, larger and more geologically active, would also have more intense volcanism and tectonics. Still, atmosphere's absence would make the planet as hostile as any other rocky body exposed to space. What would it be like to live on a planet with 10 times Earth's gravity? Gravity is one of those invisible forces that shape every aspect of our lives without us noticing. It keeps our feet planted on the ground, regulates river movement, shapes mountains, and even influences how our bodies function. We're so accustomed to Earth's gravity that it's almost impossible to imagine another reality. But what if, suddenly, we lived on a planet where this force was 10 times more intense? To begin with, the immediate impact would be on our own weight. A 150-pound person on Earth would weigh 1,500 pounds in a world with 10 times greater gravity. This isn't just a numerical issue. Muscles, bones, and organs would be crushed under this pressure. Getting out of bed would be an almost impossible task. Even standing would require unimaginable strength. On this planet, human life, as we know it, would need to be completely adapted. Body structure would have to be different. Thicker and denser bones would be necessary to support the weight, while enormous muscles would compensate for the effort. This means that if there were intelligent life in such a world, it would have very different proportions from ours. Low, robust creatures, perhaps close to the ground, would be more suitable than tall, slender beings. Biology itself would favor compact, resistant, and extremely strong forms. The circulatory system would also face an unprecedented challenge. On Earth, the heart pumps blood upward against gravity, but on a planet 10 times more massive, this effort would be monumental. A human heart simply wouldn't withstand the pressure. To survive, life would need more powerful circulatory systems, perhaps with multiple pumps distributed throughout the body, ensuring oxygen reached all parts. Breathing would follow the same logic. Human lungs function thanks to Earth's atmospheric pressure, but in a more massive world, atmosphere would also be denser. This would mean more resistance when inhaling and exhaling. Breathing would be like trying to pull air through viscous liquid. Organisms would need larger and more efficient lungs, capable of handling the suffocating environment. the impact wouldn't be restricted to bodies. Buildings would also have to adapt. On an extreme gravity planet, tall structures would be almost impossible to erect. Skyscrapers would collapse under their own weight, bridges wouldn't resist tension, and even natural mountains would have much lower height limits than on Earth. Relief would be flatter, with landscapes dominated by plains and discrete elevations. Oceans would also be different. Increased gravity would pull water with more force, keeping seas more level and waves smaller. Tsunamis, for example, would be much rarer since energy needed to lift large volumes of water would be enormous. However, tides could be intense if the planet had nearby moons or strong gravitational interactions with its star. Atmosphere would be another critical point. Extra gravity would keep gases closer to the surface, resulting in a thicker atmospheric layer. This would have two main effects: higher pressure at ground level and greater heat retention. A sunny day on this planet could become suffocating, since heat would be trapped longer. On the other hand, the planet would be better protected against gas loss to space. This dense atmosphere would also change how light behaves. The sky could appear darker or more colorful, depending on gas composition. Phenomena like sunsets and auroras would be more dramatic, spreading intense colors across the entire horizon. Even sound would propagate differently, traveling faster and deeper, since denser air would facilitate soundwave transmission. In space exploration, 10 times greater gravity would be an almost insurmountable obstacle. To launch a spacecraft from Earth requires overcoming an escape velocity of 25,000 miles per hour. On a planet 10 times more massive, this velocity would be much higher, requiring absurd amounts of fuel. In practice, civilizations in such a world might never manage to leave their planet, remaining confined to the surface. Evolutionary impacts would be equally profound. On a planet with intense gravity, natural selection would favor organisms that spent little energy moving. Crawling animals, similar to reptiles or insects, would have advantage over tall, heavy forms. Flight would be practically impossible for large creatures, since wings wouldn't have enough strength to lift bodies under such pressure. Only tiny beings could perhaps glide or make short jumps. Reproduction would also need adaptation. In humans, gestation involves development of delicate bones and muscles, but in a world of 10 times greater gravity, these fragile tissues would be crushed. This suggests life would need different reproductive cycles, perhaps producing offspring in protected environments or with reinforced body structures from the beginning. Curiously, increased gravity could offer advantages in radiation protection terms. Dense atmosphere would act as a more efficient shield against cosmic rays and solar particles. Additionally, the surface would be less vulnerable to small meteor impacts, since they would disintegrate before reaching the ground. The planet would be, paradoxically, safer against external space threats. Energy needed to move in this environment would be colossal. Simple activities, like running or jumping, would spend many more calories. To compensate, life would need abundant energy sources. Perhaps these organisms' diet would be extremely high-calorie, based on energy compounds we don't know. On an evolutionary scale, this would shape robust species with accelerated metabolism, ready to handle daily effort. Reaction time would also be different. In a high-gravity world, falls and sudden movements would be much more dangerous. A simple slip could cause fatal damage, since body weight multiplied by acceleration would be devastating. This would favor extremely cautious societies, where each step would be calculated to avoid accidents. From a geological standpoint, volcanoes and earthquakes would have altered intensities. Extra gravity would keep the crust more pressed, making eruptions less explosive, but perhaps more constant. Lava flows would be slower, squeezed by gravitational force. Hardened magma mountains wouldn't rise as much, creating flatter and more extensive volcanic landscapes. If we observed this planet's sky, we'd also notice differences in natural satellite orbits. A nearby moon could be attracted with such force that it would eventually collide with the planet. On the other hand, if it were very distant, it could be stripped from its orbit. Gravitational balance would be delicate, making planetary systems more unstable. Surface pressure would also limit certain formations' existence. Crystals and minerals would tend to be more compact, perhaps forming rocks with much higher density than we're accustomed to. This could create metallic brightness landscapes, with minerals that only form under extreme pressures. Earth's crust itself would be thinner, compressed by atmosphere and planet weight. Another curious effect would be fall time. On such a planet, objects would fall much faster. A stone dropped from hand wouldn't take seconds to touch ground, but fractions of seconds. This increased acceleration would make everything happen faster in the physical environment. Impacts, movements, shocks, the sensation would be of a heavier world in every sense, where each gesture has immediate consequences. Even water would have strange behaviors. Rivers would be narrower and deeper, since gravity would pull water with more force. Raindrops would fall faster, hitting the ground with greater impact. Clouds in turn would stay lower, compressed by dense atmosphere. The hydrological cycle would still exist, but would be faster and more violent. In the end, living on a planet with 10 times greater gravity would be like inhabiting a world of constant resistance. Every step, every breath, and every movement would be a challenge. Nothing we know on Earth would work the same way. Life would need to be completely redesigned, from its anatomy to its habits. It wouldn't be an impossible planet to inhabit, but it would certainly be a planet requiring life forms radically different than those we know. The Sun has already completed more than 20 orbits around the galaxy since it was born. When we think about the Sun's movement, the first idea that comes to mind is its daily routine of rising and setting on the horizon. On a larger scale, we also remember its role at the solar system's center, around which planets, moons, and asteroids orbit. But there's an even grander movement that often goes unnoticed. The Sun, along with all planets, is in constant journey around the Milky Way. And since its birth about 4.6 billion years ago, it has already completed more than 20 trips around the galaxy. This movement isn't something we can feel day to day, but it's happening at this exact moment. The Sun isn't stationary in space. It moves at an average speed of 514,000 miles per hour relative to the Milky Way's center. This speed is hard to imagine, but it's equivalent to covering the distance between Earth and Moon in less than half an hour. Even at this colossal velocity, a single complete revolution takes about 225 to 250 million years. This time interval is called a galactic year. While here on Earth we celebrate years based on 365 days, the solar system's cosmic clock operates on much larger scales. A galactic year represents the time the Sun takes to make a complete trip around the Milky Way's center, and since the Sun has existed for more than 4.6 billion years, we can calculate it has fulfilled this cycle about 20 times since its formation. To put this in perspective, when the Sun completed its first trip around the galaxy, Earth didn't yet exist as we know it. The planet was in formation process, with intense asteroid bombardments and bubbling internal heat. On the Sun's fifth trip, the first microscopic organisms were beginning to emerge in Earth's primitive oceans, and only on the 20th trip did dinosaurs walk the planet, long before humanity's emergence. This movement results from the galaxy's collective gravity. The Milky Way center harbors a supermassive black hole called Sagittarius A*, with mass of millions of suns. But it's not just this that exerts influence. Combined gravity of billions of stars, gas clouds, and dark matter creates the gravitational field that keeps the Sun in its orbit. It's like a galactic ballet, in which the solar system is just one of the dancers. Despite being in orbit, the Sun's path isn't a perfect circle. It describes an elliptical trajectory, undulating above and below the galactic plane throughout its journey. This means that besides moving around the galaxy's center, the Sun also oscillates vertically relative to the Milky Way's disk. This movement adds fascinating complexity to its journey, as if the solar system were surfing on a cosmic wave extending for hundreds of millions of years. This oscillation may have had important impacts on Earth's history. Some studies suggest that when crossing denser galactic disk regions, Earth may have experienced periods of greater cosmic radiation exposure and even increased comet impact frequency. Although this idea is still debated, it shows how the Sun's movement isn't just an astronomical curiosity, but may be connected to events that marked life's evolution on our planet. Another relevant aspect is that the Milky Way isn't a static stage. While the Sun completes its orbits, the entire galaxy also transforms. Stars are born in nebulae, others explode as supernovas, and entire stellar systems reorganize. This means the Sun, with each trip, crosses different neighborhoods, surrounded by stars that change over time. The space we're in today is very different from where the solar system was a few galactic trips ago. In practice, this journey means the Sun has already traveled trillions of miles in its history. Each orbit equals tens of thousands of times the distance between Earth and Sun, accumulating a trajectory almost impossible to imagine. It's as if the solar system were a constant traveler, dragging along planets, moons, asteroids, and comets in a cosmic caravan that never stops. This movement also affects how we see other stars. Since we're traveling together, nearby stars slowly change position relative to the galaxy's distant background. This displacement, called proper motion, is one of the ways astronomers use to map the Milky Way's dynamics. Thus, the simple fact that the Sun is moving helps reveal the galaxy's hidden architecture. The speed at which we move may seem immense, but it's only what's necessary for the solar system to remain in stable orbit. If it were slower, we'd be pulled toward the galactic center. If it were faster, we'd escape to interstellar space. This balance results from gravity, which has kept the cosmic dance going for billions of years, and each completed trip is more proof that this balance is maintained on almost eternal timescales. The Sun's trajectory also shows dark matter's importance. The Milky Way's visible stars don't possess enough mass to explain the galactic disk's rotation speed. It was from this discrepancy that scientists inferred dark matter's existence, an invisible substance representing most of the galaxy's mass. Thus, each Sun orbit is sustained not just by stars and gas, but also by a vastness of matter we can't see directly. During its journey, the Sun has already shared neighborhood with countless stars, some passed relatively close, on light-year scales, enough to possibly disturb comet clouds on the solar system's edge. These stellar approaches are rare, but over billions of years of travel, they become inevitable. This means that throughout its 20 trips, the Sun not only orbited the galaxy's center, but also interacted with its surroundings in subtle and cumulative ways. This colossal cycle also helps understand cosmic timescale. When the Sun completed its 10th trip, Earth's continents were grouped in a supercontinent called Pangaea. When it completed its 20th, the first mammals were beginning to diversify. Today, during its 21st orbit, we inhabit the planet, reflecting on this almost imperceptible but constant movement. Looking ahead, we can predict the Sun will continue its journey for billions of years, completing many other trips until the end of its stellar life. During this time, the Milky Way will also change. In a few billion years, it will merge with Andromeda galaxy, completely altering the scenario. The Sun's path will then be reconfigured, inserting the solar system into a new galaxy, result of two giants' fusion. This perspective helps understand that the solar system isn't isolated, but is an integral part of something larger. Our Sun, modest among hundreds of billions of stars, follows its route obeying the same physical laws that govern the entire galaxy. There exists a star so dense that a teaspoon of it would weigh billions of tons. Among all cosmic phenomena, few things impress as much as the idea of extreme density. We're accustomed to thinking about heavy objects like an anvil or an entire skyscraper, but in the universe exist bodies so compact they defy any everyday comparison. An example is neutron stars. These stars, born from the violent death of much larger ones, possess such absurd density that a simple teaspoon of their matter would weigh billions of tons on Earth. To understand how we arrive at something so extraordinary, we must remember how stars live and die. Stars like the Sun burn hydrogen in their cores, converting it to helium through nuclear fusion. This reaction releases energy and keeps the star balanced against its own gravity. But when dealing with massive stars, 8 times or more the Sun's mass, the destiny is different. Upon exhausting their fuel, they collapse under their own gravity, creating supernovas that illuminate entire galaxies. What remains after this explosion can follow 2 paths. If the star wasn't massive enough to become a black hole, collapse results in a neutron star. At this stage, all of a star's mass, often equivalent to several times the Sun's, is compressed into an object just a few dozen miles in diameter. To get an idea, this means a small city can harbor the weight of several stars. A neutron star's density is almost inconceivable. Under normal conditions, atoms composing matter have tiny nuclei surrounded by relatively distant electrons. It's this empty space between nucleus and electrons that gives matter form and volume. But in stellar collapse, this space disappears. Electrons are crushed against protons, forming neutrons compacted side by side. The result is a sphere made almost entirely of neutrons, so compact there's no more empty space. It's at this point that the teaspoon comparison arises. Imagine removing a small sample from this star. Here on Earth, a teaspoon's volume weighs a few grams when filled with water or salt. But if it were composed of neutron star material, that same spoon would have billions of tons, weight equivalent to entire mountains. This comparison directly illustrates the absurdity of these stars' density. Gravity on a neutron star's surface is equally impressive. It's hundreds of billions of times stronger than Earth's. This means any object falling onto it would be crushed and incorporated almost instantly. Light itself suffers effects from this gravity, being bent and distorted. Directly photographing a neutron star is almost impossible. Most information comes from radiation like X-rays emitted from its surface. Many of these stars are also pulsars, spinning at mind-boggling speeds. While Earth completes one rotation in 24 hours, pulsars can spin hundreds of times per second. This rapid rotation, combined with their intense magnetic field, emits radiation beams that cross space like cosmic lighthouses. Upon reaching telescopes on Earth, these signals are perceived as regular light pulses, hence the name pulsar. This regularity is so precise that some pulsars function as cosmic clocks. They emit pulses at almost perfect intervals, better than many atomic clocks. Scientists have already used this precision to study phenomena like gravitational waves and to test relativity theories. Thus, neutron stars aren't just curiosities, but valuable tools for investigating physics limits. Despite their reduced size, energy released by these stars is colossal. When 2 neutron stars collide, impact is so violent, it generates gravitational waves detectable here on Earth. These collisions also produce heavy elements, like gold and platinum, scattering them through space. In other words, part of the jewelry we wear and technology we use was forged in cosmic events involving these stars. A neutron star's surface is another point of fascination. Unlike common stars, its shell is formed by a rigid neutron crust, almost like ultra-exotic metal. This crust is estimated to be stronger than any known material, capable of withstanding unimaginable pressures. Cosmic accidents in this crust can generate explosions called starquakes, equivalent to stellar earthquakes, releasing energy on immense scales. To better understand density, a comparison is worth making. An atom's nucleus, formed by protons and neutrons, is the densest part of matter we know. A neutron star is basically composed only of these nuclei, without empty spaces. This means it's an enlarged version of what happens inside each atom, but in astronomical proportion. It's as if matter had been squeezed to its limit. This extreme density also raises questions about what happens inside these stars. Some models suggest that in their depths, neutrons may decompose into quarks, the fundamental particles composing them. This would give rise to a quark star, even more exotic and dense than a traditional neutron star. Until today, there's no observational confirmation, but it's a possibility that intrigues physicists worldwide. Light we receive from these stars is also peculiar. Many emit intense X-rays, detected by space telescopes. These emissions happen because gravity attracts gas from neighboring stars, which heats to absurd temperatures before hitting the surface. This process creates accretion disks that shine intensely in X-rays, revealing a neutron star's presence even thousands of light-years away. Some neutron stars have magnetic fields so intense they're called magnetars. These fields are trillions of times stronger than Earth's. If we were thousands of miles from a magnetar, the magnetic field would be sufficient to distort atoms in our body. Fortunately, they're very distant to represent danger. Still, they're examples of how nature can take physical forces to unimaginable extremes. Additionally, neutron stars are also perfect examples of how general relativity manifests. Their gravity is so strong that time passes slower near them compared to distant regions. This creates an environment where relativistic effects are inescapable. In this sense, studying them helps scientists confirm Einstein's theoretical predictions under conditions that cannot be recreated in Earth laboratories. Among practical implications of studying these stars is, for example, gravitational wave detection in 2017. They were generated by two neutron stars' merger, confirming theories about heavy element origins in the universe. However, neutron stars are far from eternal. Over time, some may lose energy and become even more unstable, collapsing into black holes. Thus, neutron stars are among the universe's most impressive objects. Small in size, but giant in impact, they're part of the cosmos that combines destruction, creation, and density at extreme levels. True natural laboratories for physics, forges of precious elements, and reminders that matter can assume forms beyond any everyday comparison. The largest structure in the known universe is a cosmic wall with billions of galaxies. When we observe the sky with naked eyes, stars seem randomly distributed, like luminous points on a black background. But as telescopes revealed the universe on increasingly larger scales, it became clear that the cosmos isn't empty space sprinkled with isolated objects. Galaxies aren't uniformly scattered, they cluster, form filaments, and together these filaments build colossal patterns resembling a cosmic web. Among these formations, some reach sizes so large they challenge even our notion of scale. The notion of cosmic structure emerged from sky maps that cataloged thousands of galaxies' positions. These maps show that instead of a homogeneous ocean of light, the universe organizes into clusters, connected by dark matter filaments and separated by vast voids. Each filament contains thousands of galaxies, each with billions of stars. And when these galaxy chains extend across unimaginable distances, we have so-called superclusters. Among these structures, some stand out for impressive size. This is the case of the so-called Hercules Corona Borealis Great Wall, one of the largest structures ever identified in the observable universe. It received this name because it occupies the sky region associated with Hercules and Corona Borealis constellations. Contrary to what the name suggests, it's not a solid wall, but a cosmic wall of interconnected galaxies extending across billions of light-years. This formation's dimension is almost impossible to conceive. It's estimated that its length exceeds 10 billion light-years. This means light takes 10 billion years to cross it from end to end, almost 3/4 of the universe's own age. In comparative terms, the Milky Way, with its 100,000 light-year diameter, is just a microscopic point before this cosmic wall. This structure's discovery was made through observation of gamma-ray bursts, extremely energetic phenomena associated with massive star death. These events are so bright they can be seen billions of light-years away. By analyzing where these explosions concentrated, astronomers noticed there was a space region where they seemed to align. This alignment revealed the presence of an immense galaxy concentration, the cosmic wall. The methodology itself draws attention. It's not about seeing the wall as an illuminated galaxy wall, but inferring its existence from event density observed in that region. It was like perceiving a mountain range's silhouette amid fog, not because we see its mountains directly, but because we recognize the contours they project. This cosmic detective work was fundamental to reveal that the universe contains colossal scale structures. The notion of a cosmic wall also helps understand how the universe evolved since the Big Bang. Cosmology models suggest that shortly after initial expansion, small density fluctuations in primordial matter began amplifying. Gravity made denser regions attract extra matter, forming filaments. Over time, these filaments connected, giving rise to the largest known structures. The Hercules Corona Borealis Great Wall is the visible result of this process at its maximum scale. Study of these giant formations is important because it tests the cosmological principle. This principle, basis of most universe models, states that on large scales, the cosmos is homogeneous and isotropic, that is, equal in all directions. But structures as extensive as this wall seem to challenge this idea, since they concentrate matter in volumes much larger than expected. This generates intense debates among astronomers and cosmologists. To get an idea of impact, some calculations suggest structures larger than 1.2 billion light-years larger would already be difficult to explain within our current models. The Hercules Corona Borealis Great Wall is almost 10 times larger. This discrepancy raises questions. Are our theories about galaxy growth incomplete? Does the universe have density variations on even broader scales than we imagined? Even if these questions remain open, the cosmic wall's existence helps map the universe's cosmic web. It's just one piece of a puzzle that includes other colossal structures, like the Sloan Great Wall, the Boötes Wall, and the Laniakea supercluster, the latter home to our own Milky Way. Together, they form a network connecting billions of galaxies in patterns resembling a living organism's veins. Voids between these structures are equally impressive. While walls and filaments concentrate matter, voids are enormous regions with very few galaxies. The contrast between dense and almost desert areas creates a pattern resembling cosmic foam. Earth, along with the Milky Way, inhabits one of these filaments, neighboring an immense void. This shows us that our planet's position is just a point in a network extending throughout the observable universe. The idea that the universe organizes in such vast patterns wasn't evident until a few decades ago. It was only with extensive surveys, like the Sloan Digital Sky Survey, which mapped millions of galaxies, that these filaments began being drawn in detail. The Hercules Corona Borealis Great Wall represents this effort's culmination, revealing that there are structures whose scale approaches the universe's own age. The cosmic wall's grandeur also helps calibrate dark matter and dark energy models, components representing most of the universe. These invisible elements shape how matter organizes on large scales. Therefore, studying where galaxies are and how they align is a way to map the invisible. The wall, in this sense, is a clue about how gravity and cosmic expansion interact over billions of years. Another curiosity is that despite the name, the wall isn't a solid barrier. It's a concentration of galaxies, interconnected by gravity, separated by voids, but sufficiently close to form a continuous structure. If it were possible to cross it, we'd find superclusters, spiral, elliptical, and irregular galaxies, each with billions of stars and probably trillions of planets. The notion of scale here surpasses any terrestrial comparison. Study of the cosmic wall also depends on sophisticated light analysis techniques. Each galaxy emits signals that can be interpreted to determine its distance. By compiling this data, astronomers build three-dimensional universe maps. These maps, when viewed in perspective, reveal the filament and wall pattern. It's like drawing the cosmos's geography, but on scales that challenge imagination. The complexity of these maps shows we're still only scratching the surface of what exists. New telescopes like James Webb and the Vera Rubin Observatory promise to reveal even more details, expanding galaxy catalogs and possibly identifying other structures as large or as larger than the Hercules Corona Borealis Great Wall. With each new data point, the cosmic web's image becomes more precise and surprising. Additionally, these discoveries have direct effect on how we think about galactic evolution. Galaxies in dense regions, like those composing the wall, probably evolve differently from those isolated in cosmic voids. They suffer more frequent interactions, mergers, and matter exchanges. This dynamic environment accelerates new star formation and modifies galactic chemistry over billions of years. The revelation that there exists a formation with billions of interconnected galaxies is by itself a landmark, as it redefines what we consider possible in terms of cosmic organization and puts Earth's place within this colossal fabric in perspective. What would happen if a coin-sized black hole appeared on Earth? If we look at a simple coin, its dimension is so small it fits in the palm of our hand. Now imagine that suddenly this coin were replaced by a black hole. The contrast couldn't be greater. An invisible object, tiny in physical size, but with such tremendous mass it distorts space around it. The idea may sound like fiction, but it's an exercise that helps reveal black holes' extreme nature and their devastating effects. A black hole isn't defined by its physical size, but by the mass it concentrates in a tiny space. The coin size refers to the so-called event horizon, the limit beyond which nothing can escape. For a black hole to have this scale, its mass would be equivalent to Earth's entire mass compressed into this small point. In other words, a coin-size object, but with an entire planet's gravity suddenly appearing in our world. The impact would be immediate and devastating. Gravity is proportional to mass, and the black hole of this size would exert colossal attraction on everything around it. Within fractions of seconds, nearby objects would be sucked toward the event horizon. This includes air, soil, buildings, people, rivers, and mountains. Nothing would have time to react. Matter would be swallowed and compressed to densities impossible to reproduce in any other scenario. As the black hole began swallowing matter, an accretion disk would form, a structure of dust and plasma spinning at extremely high speed around the event horizon. This disk would heat to millions of degrees, emitting intense radiation, including X-rays. The place where it emerged would transform into a point of blinding and deadly light, even though the black hole itself would be invisible. Gravitational attraction would grow exponentially as the black hole consumed more matter. First, it would swallow local structures, buildings, cities, forests. Then Earth's crust would be torn, releasing magma in colossal quantities. The planet made of layers would become a feast of matter for the new cosmic predator. Within hours, entire continents would be sucked into a point in space smaller than a coin. There would be no escape for anything nearby. Atmosphere itself would be pulled, spinning around the black hole like a flaming spiral. Winds of thousands of miles per hour would cross the planet toward the destruction center. Pressure and energy released would make Earth cease being a stable environment and transform into a plasma ball spinning around a devouring core. Physics behind this process would leave no room for balance. Once the black hole began consuming mass, its power would only increase. With each ton of matter swallowed, its gravity would become more intense. The process would be self-sustaining, a cascading collapse. The entire planet would become unstable within days, with its mass being sucked into an invisible and compact object. Over time, Earth would cease existing as we know it. The mantle and core would be devoured, and the black hole would become increasingly massive. It wouldn't stop at the surface. Its gravitational field would penetrate to the planet's center, tearing away entire layers. Earth's rotation would be abruptly interrupted, and the planet would break apart while being absorbed. This process wouldn't be silent. Energy released would be immense, comparable to millions of atomic bombs per second. X-rays and gamma radiation would escape from the accretion disk, sterilizing any life form not yet destroyed by gravity. The sky would fill with blinding light, and atmosphere would burn in a storm of energetic particles. Life, on any scale, would have come to an end. And it wouldn't just be Earth suffering. A black hole's gravitational influence grows with distance. Once the planet were completely swallowed, the black hole would inherit its total mass, further increasing its reach. The Moon, linked to Earth by gravity, would also be pulled inside. Then other solar system planets could have their orbits disturbed, depending on position and energy released during collapse. This would transform not just Earth, but the entire solar system's balance. Planets could be ejected from their orbits, diverted away from the Sun, or even attracted to the black hole's spiral. The delicate gravitational ballet keeping worlds in harmony would be destroyed, giving way to a chaotic and unstable system. Beyond immediate consequences, there's also the question of what would happen to the black hole itself. Once formed and fed by Earth, it would become stable and continue existing indefinitely. Unlike stars which have life cycles, black holes only disappear through evaporation via Hawking radiation, a process taking trillions of years. Thus, the black hole would remain as a permanent scar from Earth's disappearance. From a scientific standpoint, this scenario helps understand why black holes are considered the universe's most extreme objects. They not only challenge our imagination, but also our physical theories. Density, space distortion, and time frozen at the event horizon are concepts we still don't fully comprehend. The idea of such an object appearing on Earth is an exercise showing the difference between everyday and cosmic. Size comparison is also fundamental for visualizing contrast. Earth, with its 7,900-mile diameter, would be swallowed by an invisible point, just a few centimeters in diameter. This is black hole's power, maximum mass concentration in minimum space. The coin size isn't just a curious image, but description of one modern physics's most extreme paradoxes. It's important to note this scenario is purely hypothetical. Black holes can't simply appear from nothing. They're formed from very massive star collapse, a process occurring in specific space regions. Still, imagining their sudden presence on Earth helps us better understand their destructive nature and how fragile the balances keeping a planet like ours safe are. This type of reflection also serves as pedagogical tool. By thinking about how a coin-sized black hole would swallow Earth, we better perceive the scale of forces governing the universe. Gravity, which for us seems just to keep feet on ground, on cosmic scales, becomes the most powerful force, capable of transforming worlds into nothing in moments. While stars shine and planets orbit in relative calm, black holes represent extremes. They're physics' end-of-line points, regions where known laws cease making sense. The image of a coin-sized object devouring Earth is the clearest way to understand what the expression "bending space-time" means. Earth's collapse toward a black hole would leave no traces of its history. Forests, oceans, cities, and even the core would be reduced to energy particles, spiraling until disappearing beyond the event horizon. Nothing would escape, not even light trying to reflect the scene. The entire planet would be erased in an inevitable process. There are rogue planets wandering through space without a star to orbit. When we think of planets, the immediate image is of worlds spinning around a star, illuminated and heated by radiation they receive from it. However, not all follow this pattern. Some, known as rogue or interstellar planets, don't orbit any star. They wander alone through deep space without a sun to guide them, without fixed orbit, immersed only in cosmos's darkness and cold. These solitary worlds conform in two main ways. Some are born around stars like any other planet, but are expelled from their systems by violent gravitational interactions. Others perhaps form directly from gas clouds, similar to the process generating stars, but without reaching sufficient mass to initiate nuclear fusion. In both cases, the result is the same: a planet condemned to follow its own path through the galaxy without defined home. Numbers suggest these objects aren't rare. Studies indicate that for every star in the Milky Way, there may be up to 2 rogue planets. If this estimate is correct, this means hundreds of billions of loose worlds, invisible to most telescopes. The galaxy's vastness isn't just dotted by stars and their systems, but also by isolated planets hidden in darkness. Detecting them, however, is an enormous challenge. Without a star to illuminate their surface, these planets don't reflect enough light to be seen directly. Main observation techniques depend on rare events, like gravitational microlensing, where the planet's mass distorts a distant star's light, revealing its presence. These are ephemeral moments, but they allow confirming these invisible travelers' existence. The first confirmed candidates were found in the early 2010s. An example is the object called CFBDS IR 2149-0403, detected about 100 light-years from Earth. It appears to be a giant gas planet, loose in interstellar space. Other candidates were identified in young star clusters, where gravitational dynamics make newly formed planet ejection more likely. These discoveries gave shape to a category that was previously only speculation. Life on these rogue worlds would be almost impossible on the surface, at least under Earth-like conditions. Without energy from a nearby star, the temperature would drop to levels near absolute zero. However, this doesn't mean they're totally dead. If large enough, they can retain internal heat generated by their element's radioactivity or their own mass's gravitational pressure. In this case, heated underground oceans could exist under thick ice layers. This hypothesis is especially intriguing. In worlds like Europa or Enceladus, Jupiter and Saturn's icy moons, underground oceans are believed to exist thanks to internal heat. Rogue planets, even solitary, could harbor similar conditions. Thus, a star's absence doesn't completely eliminate the possibility of habitable environments, albeit in protected niches far from the frozen surface. Another fascinating characteristic is their gravitational interaction. A rogue planet passing near a stellar system could disturb its planet's orbits, perhaps even capturing moons or small bodies. In extremely rare cases, it could be imprisoned by a star, gaining a new orbit and restarting its history. These cosmic encounters would be silent, but loaded with consequences for worlds they touched. These planets' size varies widely. Some are gas giants, comparable to or larger than Jupiter. Others may have masses similar to Earth's. Diversity is great, and since they're not illuminated, most remain beyond detection reach. Each new gravitational microlensing event opens the chance to reveal one of them, but always in small numbers, leaving much of this hidden universe. Rogue planet formation also helps explain how planetary systems evolve. Many simulations show that body ejection is a common process during a star's first millions of years of life. Planets compete for space, collide, are launched into unstable orbits. What remains around the star is just a fraction of what was born. Rogues, therefore, are witnesses of this primordial chaos, echoes of systems that organized at the cost of expelling part of their matter. Astronomers estimate billions of rogue planets wander the Milky Way alone. This means the chance of one being relatively close to us isn't negligible. Perhaps one exists just a few dozen light-years away, invisible, crossing darkness without our awareness. On cosmic scales, they're silent neighbors sharing our galaxy. If some rogue planet passed near the solar system, we'd feel its influence. Even without colliding, its gravity could destabilize orbits, displace comets from the Oort cloud, or alter asteroid paths. Though unlikely, this scenario shows how these solitary bodies, despite being invisible, carry enough power to shape inhabited worlds' destinies. Rogue gas giants are especially interesting. Without a star's radiation, they can still emit infrared heat, result of their own gravity's contraction. It's this heat that, in some cases, allows telescopes to capture their presence. This radiation, though weak, is the mark that the planet is alive in energetic terms, even without nearby starlight. There's also the question of their atmospheres. A Jupiter-sized rogue planet could retain hydrogen and helium for billions of years, maintaining a thick and active atmosphere. Smaller rocky planets would probably lose their gases to space, becoming frozen deserts. This difference shows how mass is a decisive factor in a solitary planet's survival. Recent studies suggest that under certain conditions, even rocky planets could preserve atmospheres if they had a dense hydrogen layer. This layer would function as a blanket, trapping internal heat and allowing relatively mild surface temperatures. Though rare, this means we can't completely rule out habitable worlds' existence even without a star. Astrobiology, therefore, looks at these planets with interest. If underground oceans or insulating atmospheres can sustain stable environments, microorganisms could exist on rogue planets. This would enormously expand the notion of habitability, showing that life doesn't depend exclusively on a star's energy. The cosmos could be filled with biological niches hidden in invisible worlds. Detection of these planets will also become more common with next-generation telescopes, like Nancy Grace Roman and future infrared observatories. They'll be able to record microlensing events more precisely and capture these bodies' weak radiation. With this, we can not only confirm their abundance, but also study their composition and atmospheric properties. Each rogue planet found is a piece in a larger puzzle, how the galaxy distributes its matter. If there really are billions of them, this means a significant fraction of the Milky Way's mass is hidden in these darkened worlds. They would be the invisible part of cosmic accounting, as relevant as stars and entire galaxies for the galaxy's gravitational balance. This perspective also changes our view of what it means to be a planet. Traditional definition associates it with a star, but rogues break this link. They show that being a planet doesn't require a sun. It's enough to be a body with sufficient mass to be shaped by its own gravity and wander through space. The concept expands, and diversity becomes even more impressive. Sound doesn't propagate in space, but some galaxies vibrate as if emitting musical notes. When we talk about outer space, the first idea that arises is absolute silence. Science fiction films may exaggerate sounds of explosions and engines, but in reality, space is a void where sound, as we know it on Earth, simply cannot exist. Sound needs a medium to propagate: air molecules, water, or any substance that vibrates in response to a pressure wave. Without these particles, there's no vibration, and without vibration, there's no sound. This absence of sound propagation in space was confirmed by basic physics and reinforced by experiments. Astronauts in orbit, for example, can only communicate by radio, never by shouts or snaps, because vacuum doesn't transmit acoustic waves. Space, therefore, is mute in the conventional sense. But this isn't the whole story. The universe, even in silence, harbors forms of vibration that approach what we call sound. The key lies in the fact that not all cosmic regions are totally empty. Galaxies, nebulae, and clusters contain rarefied gases composed of atoms and highly energized plasma. This material isn't dense enough to carry sound like on Earth, but can vibrate on enormous scales. These vibrations, detected by sensitive instruments, resemble sound waves. They are not notes we could hear with our ears, but pressure variations that can be translated into audible frequencies. One of the most famous examples was recorded in the Perseus cluster, about 250 million light-years away. The Chandra Space Telescope detected ripples in hot gas permeating the cluster, caused by the supermassive black hole at its center. These waves had characteristics similar to sound waves, with a wavelength so large it would equal 57 octaves below middle C on a piano. In practical terms, it's a note we could never hear directly, but exists as real vibration in cosmic plasma. These notes are extraordinarily low. While human ears can perceive sounds between 20 and 20,000 hertz, vibrations in Perseus had a frequency of a single oscillation every 10 million years. This means they're incredibly slow sounds, almost impossible to conceive. Still, from a physics standpoint, they obey the same laws governing a violin's or voice's sound. The difference lies in scale. Instead of strings or vocal cords, entire gas clouds vibrate under black holes' effect. These waves' origin is linked to black holes' energetic activity. Though known for devouring matter, they also release colossal energy jets, capable of crossing thousands of light-years. These jets push surrounding gas, creating pressure waves spreading through the interstellar medium. The process is similar to sound produced by a speaker, which pushes air and generates waves reaching our ears. For astronomers, these waves reveal how black hole energy is distributed in space and how they influence galaxy formation. By analyzing gas vibration, scientists can measure its density, temperature, and dynamics, better understanding universe evolution on large scales. Another fascinating aspect is that these waves can be translated to audible frequencies, creating what we call sonification. By artificially accelerating oscillations, transforming millions of years into seconds, researchers can hear the universe. The result is a low and ethereal sound like distant chanting. It's not literal reproduction, but mathematical transposition, allowing us to experience, sensorially, something existing on scales far beyond our perception. This practice has already been applied to diverse cosmic objects. Waves detected in black holes, pulsars, and even nebulae were converted to sounds, creating true space soundtracks. For science, this is a resource translating data into accessible language. Cosmic music isn't imagination's fruit, but physics in action. However, it's important to highlight that interstellar space is still too rarefied to transmit sound in the common sense. These are phenomena measured by instruments sensitive to pressure and radiation variations. What we call cosmic sound is therefore a useful metaphor. We don't hear with ears, but with telescopes and calculations. Curiously, this notion approaches how ancients viewed the cosmos. Philosophers like Pythagoras spoke of music of the spheres, the idea that celestial bodies in movement produced inaudible harmonies. Today, we know planets don't sing, but galaxies really vibrate. The difference is it's not mysticism, but physical waves recorded and analyzed in laboratories. myth transformed into science. These vibrations also bring clues about black holes' role in regulating cosmic energy. Without jets agitating gas, many galaxies would have formed differently. The sound we hear through plasma is in practice the record of black holes' action shaping the universe. It's a reminder that even space's silence is full of hidden stories. In technical terms, these waves are part of what we call astroseismology. Just as scientists study vibrations inside Earth to understand its structure, or seismic waves in the Sun to know its internal dynamics, we also analyze waves on galactic scales. Each vibration is an echo of invisible energetic processes, allowing mapping of phenomena that couldn't be observed otherwise. Another example comes from pulsars, neutron stars spinning at high speed. Their regular rotations produce radiation pulses resembling a cosmic metronome's beats. Though not sound in the classic sense, these periodic signals can be converted to audible frequencies. The result is a tick-tock of stellar origin, a kind of universe's natural percussion. And however abstract these waves may seem, they connect directly with our experience. Sound, after all, is just a form of wave. What differentiates a melody on piano and vibration in Perseus is scale and medium where they propagate. The physics is the same. The light we see from some stars left them before Earth even existed. When we look at the night sky, we see luminous points apparently motionless, as if they were lanterns hung on a black canvas. But the truth is that each star is at a colossal distance, and the light reaching us is a messenger from the past. In some cases, this past is so remote that radiation left its source before Earth even existed. This means that when observing the sky, we're not just looking into space, but traveling through time. This concept becomes clearer when we think about light speed. Nothing in the known universe is faster. 186,000 miles per second. Still, even at this velocity, light takes years, centuries, or millions of years to cross cosmic distances. That's why astronomers use light year as a distance measure. A star 500 light-years away is showing us how it was 500 years ago, not how it is today. When we expand this scale, the effect becomes even more impressive. There are stars so distant that their current light began traveling billions of years ago. For comparison, Earth is about 4.5 billion years old. This means some stars we observe were already shining in the cosmos before our planet's birth, even before the solar system formed. Each photon reaching us is a relic older than the world we live in. Among these objects are the most distant galaxies we can detect. The light we see from them began its journey shortly after the Big Bang, when the universe was still in its initial stages. Modern telescopes like James Webb can capture these signals, allowing scientists to study how the first stars and galaxies emerged. The oldest known stars belong to a category called Population II stars. They formed when the universe was still young, composed almost entirely of hydrogen and helium, since heavier elements hadn't yet been created in stellar explosions. Some are estimated to be over 13 billion years old. Light reaching us began traveling before our planet's formation. A notable example is star HD 140283, nicknamed the Methuselah star. It's estimated to be about 14 billion years old, almost as old as the universe itself. Although there are error margins in calculations, it's likely one of the oldest stars ever observed. When its light reaches us, what we see is a portrait from an era before our planet's formation. It's as if we were looking at a living archive of the cosmic beginning. Another example is quasars, active nuclei of distant galaxies powered by supermassive black holes. Their light travels over 10 billion years before reaching Earth. This means the quasars we observe today already existed when the universe was less than 1/10 its current age. the energy we capture is an echo from times when not even the Milky Way had fully formed. This notion of looking back in time is central to astronomy. Each star, each galaxy, and each distant luminous point is a record of a specific universe phase. Astronomers, studying these signals, are literally building a cosmic timeline. The farther you observe, the earlier in universe history you see. It's as if space were also a vast time archive. The reason for this is that the universe is incredibly vast. The nearest star to us, Proxima Centauri, is just over 4 light-years away. But many stars visible to the naked eye are hundreds or thousands of light-years away. And with telescopes, we reach billions of light-years distance. At each step of this ladder, time rewinds on scales that challenge our intuition. For example, light from Andromeda galaxy, visible as a faint spot in the sky, takes about 2.5 million years to reach us. When it left there, the first hominids were just emerging on Earth. But there are even more distant galaxies, whose light began its journey when there weren't even planets like ours. It's in these cases that the phrase gains strength. Some stars were already emitting light long before Earth existed. This delay in light's arrival also means we may be observing stars that no longer exist. If a star thousands of light-years away exploded, radiation from its death is still on its way and will only be visible to us in the future. Thus, part of the sky we see may be a portrait of a past that no longer corresponds to the universe's real present. This phenomenon creates a curious paradox. We never see the universe as it is, but always as it was. Even sunlight, which is only 93 million miles away, takes about 8 minutes to reach us. This means we technically always live a few minutes behind the sun's present. With distant stars, this delay transforms into millions or billions of years. The Hubble Space Telescope has already revealed galaxies whose light left over 13 billion years ago, and with James Webb, the frontier expanded even further, allowing observation of light from the first stars, known as population 3 stars. These stars were responsible for creating the first heavy elements, fundamental for rocky planet formation like Earth. In other words, by observing this ancient light, we're seeing the origin of ingredients that would later compose our world. The physics involved in this process is straightforward, but its consequences are profound. Light speed is finite, and this transforms the universe into an immense time tunnel. The more distant an object is, the older the image we receive from it. That's why astronomers say their telescopes are also time machines. Each observation is a journey to the past. On Earth, we're accustomed to seeing the immediate present, but in the cosmos, visual information always arrives late. It's this delay that allows scientists to study cosmic evolution. By observing stars at different distances, they build an evolutionary timeline of the universe. It's as if we were looking at a photo album, where each image shows a different stage: childhood, adolescence, maturity. But in this album, images all arrive simultaneously, projected in the night sky. For us lay people, this notion transforms the act of observing the sky into something even more fascinating. When we see a star shine, we may be witnessing light that began its journey when the universe was still organizing itself. Before Earth, before the sun, before everything we know, cosmic rays constantly cross our planet, coming from distant stellar explosions. When we talk about radiation, we often think of something nearby: medical equipment, nuclear plants, or even sunlight. But space sends Earth a much older and more powerful form of radiation: cosmic rays. Invisible, silent, and incessant, they cross the atmosphere and hit our planet every second. And most impressive is that many were born in stellar explosions that occurred thousands or millions of light-years away. These particles aren't light beams, but subatomic projectiles, composed mostly of protons, electrons, and atomic nuclei, traveling at speeds close to light. They're launched into space by extreme events: supernovas that destroy massive stars, active galaxy nuclei powered by black holes, and even collisions between neutron stars. Each of these events functions as a cosmic furnace, accelerating particles to energies far exceeding those produced by any human accelerator. On Earth, we have the Large Hadron Collider in Geneva, capable of accelerating particles to immense speeds. Still, cosmic rays arrive with energies millions of times greater. Their projectiles so energetic, they challenge our understanding. A single cosmic ray can carry energy equivalent to a moving baseball, concentrated in a tiny particle. This disproportion shows how violent the phenomena that originate them are. Upon hitting the atmosphere, these rays collide with oxygen and nitrogen atoms, creating cascades of secondary particles. This effect is called atmospheric shower. With each impact, electrons, muons, and other particles emerge, spreading in different directions, crossing air layers and even the ground. This means that right now, cosmic rays are passing through you, crossing your body without you noticing. Despite this constant contact, cosmic rays don't represent immediate danger at common levels. Earth's atmosphere and magnetic field function as protective barriers, absorbing most energy before it reaches the ground. But their presence is sufficient to leave marks. In electronic circuits, for example, they can generate spontaneous failures, interfering with satellites, planes, and even supercomputers. A famous example of this effect happened in 2003, when an error in an electronic voting system in Belgium was attributed to a cosmic ray that altered a bit in computer memory. There's no way to completely avoid this risk. Any electronic system exposed to space or at high altitude can be hit. That's why engineers must design equipment with redundancies and automatic corrections, taking into account the invisible particle rain that never ceases. Beyond technical failures, cosmic rays also represent risk for astronauts. Outside Earth's atmospheric and magnetic protection, exposure to this radiation is much greater. On long journeys, like to Mars, astronauts may accumulate dangerous doses, capable of increasing cancer risk or causing nervous system damage. That's why research on space shielding is so important for interplanetary exploration's future. But cosmic rays, besides representing a threat, are also a precious information source. By studying them, scientists can infer the nature of events that generated them. Composition, energy, and direction of these particles reveal clues about stellar explosions, black hole jets, and cosmic collisions. Observatories built to detect these particles are impressive. In the Mendoza Desert, Argentina, stands the Pierre Auger Observatory, covering an area larger than New York City. It uses thousands of detectors spread across the ground, plus fluorescence telescopes to observe atmospheric showers created by cosmic rays. This data helps trace the map of high-energy particles constantly bombarding our planet. Another notable facility is the Fermi Space Telescope, which, from space, detects gamma rays associated with cosmic ray origins. Together, terrestrial and space observatories create an information network, allowing investigation of the cosmos differently from light observation. The mystery, however, isn't yet solved. Although we know supernovas and black holes contribute to cosmic ray production, the most energetic known particles, called ultra-high energy, seem to have still unknown origins. They arrive with such absurd energies that no known source can completely explain them. Finding their origin is one of modern astrophysics' great challenges. Beyond origin, there's also the journey question. Since cosmic rays are charged particles, they suffer deviations when crossing magnetic fields of galaxies and intergalactic space. This means when arriving at Earth, their original direction has often been altered. Tracing the path back to the source is almost impossible. It's like trying to discover a leaf's origin carried by a storm. This elusive character doesn't prevent, however, their influence being noticed on cosmic scales. Cosmic rays can affect cloud formation in Earth's atmosphere, acting as condensation nuclei. Some studies suggest that even with small effects compared to other factors, they may have indirect role in Earth's climate. On even larger scales, cosmic rays contribute to galaxy evolution itself. By interacting with interstellar medium, they alter space's chemical composition, helping spread heavy elements. These elements are, in turn, raw material for new stars and planets. Thus, the constant particle rain isn't just an invisible detail, it's part of a cosmic cycle that renews the universe. Cosmic rays are so energetic, they test laws under conditions we can't reproduce in laboratories. Therefore, analyzing their behavior allows verifying theories about elementary particles, quantum fields, and even hypotheses about extra dimensions. Knowledge about this type of particle is fundamental for human life, with medical implications included. In hospitals, imaging equipment and radiotherapy must be calibrated to handle occasional cosmic ray interference. This helps us, for example, effectively understand radiation effects on the human body in the future of space travel, when humans will spend months or years outside terrestrial protection. Even in commercial aircraft, passengers are exposed to slightly higher doses of cosmic radiation than on the ground. This is because thinner atmosphere at high altitudes offers less protection. Pilots and crews accumulate extra doses throughout their careers, which is why this exposure is monitored in many countries. With all this, it's clear that cosmic rays are a central phenomenon for understanding the connection between Earth and universe, since they connect distant star explosions to effects in our computers, planes, and even climate. They're simultaneously a threat, a scientific tool, and a reminder that we're not isolated in space. Earth's magnetic field has reversed many times throughout history. The planet we live on isn't just a rock sphere spinning in space. It's also enveloped by an invisible shield, a force bubble called magnetosphere, which protects Earth from solar radiation and cosmic winds. This magnetic field, generated by liquid iron movement in the planet's outer core, functions as a barrier against charged particles that could destroy our atmosphere and expose the surface to lethal radiation levels. Without it, life as we know it would hardly exist. However, this field isn't static. It pulses, changes intensity, and from time to time does something even more surprising: reverses its polarity. The magnetic North Pole becomes the South Pole, and the South Pole becomes the North Pole. For us, accustomed to the idea of a planet with fixed poles, this reversal may sound strange, but it has already happened hundreds of times throughout Earth's geological history. It's a natural process, result of the planet's interior turbulent dynamics. Everything's origin lies in the so-called terrestrial dynamo. Earth's outer core is formed by iron and nickel in liquid state, constantly moving due to heat from the solid inner core and planet rotation. This movement generates electric currents, which in turn produce the magnetic field. But this process isn't perfectly stable. It's chaotic, full of fluctuations, and over millions of years can completely reorganize, causing pole reversal. Evidence of this phenomenon is recorded in rocks. When lava cools and solidifies, magnetic minerals it contains align with the existing field at that moment. These fossilized records function as little natural compasses, keeping Earth's magnetic orientation from past eras. Studying underwater mountain chains and volcanic deposits, geologists found clear reversal patterns, showing the field has inverted many times. The interval between these reversals isn't regular. Sometimes the field remains stable for tens of millions of years. In other periods, reversals happen at intervals of just a few 100,000 years. The last major reversal occurred about 780,000 years ago and is known as the Brunhes-Matuyama reversal. Since then, the field has shown weakening signs, leading some scientists to speculate if we're approaching a new change. But what would this process be like in real time? Contrary to what many imagine, the reversal is a gradual transition, which can take thousands of years. During this period, the magnetic field weakens, fragments into multiple temporary poles, and only then stabilizes in a new configuration. For those living on the surface, the effect wouldn't be an instant apocalypse, but rather a long phase of magnetic instability. Field weakening has direct consequences. The weaker the magnetosphere, the more charged particles from the sun can penetrate. This means auroras visible at much lower latitudes than today, transforming the sky into a frequent luminous spectacle. But it also means satellites, power grids, and communication systems would be more vulnerable to solar storms, since natural protection would be less efficient. For life on Earth, the effects would be different. Animals that use magnetic field for orientation, like migratory birds, sea turtles, and even bacteria, could temporarily become confused. This would generate ecological imbalances in some species, but wouldn't be sufficient to extinguish them. Human life, protected by technologies and atmosphere itself, wouldn't run direct risk of disappearing, though our electricity-dependent infrastructure would be much more fragile. Studies indicate that during a reversal, the field doesn't completely disappear, but becomes irregular and fragmented. This creates areas with stronger magnetism and others almost without protection, called magnetic anomalies. Today, we already know one of these regions, the South Atlantic anomaly, where the field is weaker and satellites suffer greater damage due to radiation. In a reversal, phenomena like this could spread across the globe. A fascinating detail is that not all reversal attempts are completed. There are records of geomagnetic excursions, where the field initiates a reversal, partially changes its orientation, but then returns to the previous pattern. This shows that the terrestrial dynamo is even more unpredictable than thought, and that the reorganization process can fail or be interrupted. Earth's magnetic history is therefore marked by both successes and setbacks. From a geological standpoint, reversals don't seem linked to global catastrophes. There's no evidence that major extinctions coincided with these events. This suggests that, although important for modern technology, reversals are relatively neutral phenomena for life in the long term. Additionally, the terrestrial dynamo is such a chaotic system that predicting its behavior is as great a challenge as predicting climate thousands of years from now. Therefore, it's practically impossible to know when the next reversal will happen. What's known is that the magnetic field is currently weakened by about 10 to 15% compared to its historical average and continues changing slowly. This may mean a reversal is on the way, but may also indicate just normal fluctuation. Modern instruments like satellites monitoring the magnetic field in real time help map these changes. Missions like SWARM from the European Space Agency track magnetosphere intensity and structure, allowing monitoring of its evolution with more precision. These observations are essential for distinguishing between simple variation and true reversal beginning. If reversal begins, humanity will have to deal with a temporarily more vulnerable Earth. Power transmission lines could suffer overloads during solar storms. Communication and navigation satellites would be damaged more frequently. Space travel would require additional shields to protect astronauts. On a practical scale, it would be a technological challenge, not a natural catastrophe in the traditional sense. Despite concerns, it's important to remember that Earth's atmosphere would still continue being a powerful shield. Even with a weak magnetic field, it would absorb much solar radiation. Surface life wouldn't be exterminated, just exposed to higher cosmic energy levels in some regions. The most significant changes would be seen in the sky, with auroras shining in unexpected places, and in infrastructure which would need constant adaptations. Over the last 60 million years, scientists identified more than 100 complete reversals. This shows the phenomenon is common on geological scale. The planet has already gone through them countless times and will continue going through them. This contrast between geological scale and human scale is what makes the topic so fascinating. For the planet, reversals are normal events without drama. For us, who are here only for a blink in Earth's history, they seem extraordinary, almost apocalyptic moments. The difference lies in the time we measure events, millions of years for geology, few generations for humanity. What would it be like if we could travel to Jupiter's core? Traveling to Jupiter's core is an idea that challenges not just engineering, but also imagination. The solar system's largest planet is a gaseous colossus more than 300 times more massive than Earth, with an atmosphere in constant movement. There's no solid surface to land on, just increasingly dense layers of gases and pressures that increase with each mile of depth. Still, imagining a journey to its interior takes us to explore some of the most extreme environments science has ever described. The descent's beginning would be through its upper atmosphere, composed mainly of hydrogen and helium. This region is marked by colorful clouds we observe from telescopes and probes, forming bands and swirls. Here lives the famous Great Red Spot, a storm larger than Earth that has lasted for centuries. Entering this layer would be like diving into an infinite gas ocean, where no fixed horizon exists, just a sky that mixes with invisible ground itself. Just below the outermost clouds, pressure would begin increasing rapidly. On Earth, at sea level, pressure is 1 atmosphere. On Jupiter, every few miles, it grows relentlessly. What would be crushing for us at oceanic depths, on Jupiter happens in the first moments of descent. The sensation would be like diving into an endless sea, where each meter means increasingly greater weight on the structure. With increasing pressure, gases also change behavior. Hydrogen, instead of remaining light and diffuse, becomes denser, transforming into thick fluid. Colorful clouds dissolve into an opaque environment where sunlight can't penetrate. Temperature, already high due to proximity to the planet's energetic core, rises rapidly, reaching thousands of degrees Celsius. The journey becomes not just dark, but incandescent. At this point, winds reach absurd speeds. It's estimated that internal atmospheric currents may exceed hundreds of miles per hour, much more intense than any terrestrial hurricane. These convection currents transport heat from interior to upper layers, sustaining constant movement we see from orbit. Traveling through this region would be like crossing an endless whirlwind where no calm exists, just incessant energy flow. As we dive deeper, pressure continues rising, reaching millions of times Earth's at sea level. Here, hydrogen undergoes one of planetary physics' most extraordinary transitions. It transforms into metallic hydrogen. Instead of being a gas, it behaves like liquid metal, capable of conducting electricity. This gigantic layer is responsible for Jupiter's colossal magnetic field, the solar system's strongest. This magnetic field, in turn, creates radiation belts so intense that any probe or ship would be fried before even approaching this region. Charged particles spin around the planet, forming spectacular polar auroras, but making the environment lethal for any conventional electronics. It's like traveling inside a natural reactor, powered by forces we can't reproduce in laboratories. The deeper we descend, the more metallic hydrogen accumulates in a deep and unimaginable ocean. This layer has no Earth equivalent. It's estimated its thickness is tens of thousands of miles, forming a boundaryless sea compressed by Jupiter's intense gravity. Navigating this ocean would be impossible. Any object would be crushed and melted in seconds. At this oceanic depth's deepest limit, scientists believe Jupiter's core exists, but what exactly lies there is still a mystery. Models suggest the core may be rocky, formed by silicates and iron, like terrestrial planets, but surrounded by exotic ice layers and metals under extreme pressure. Other models indicate there's no defined core, but rather a gradual transition to a dense mixture of materials dissolved in metallic hydrogen. If there were a solid core, reaching it would mean facing pressures exceeding 100 million atmospheres. It's like concentrating entire mountains' weight on each square inch. Temperature would also be unimaginable, reaching about 54,000 degrees Fahrenheit, much hotter than the sun's surface. Any terrestrial material, natural or constructed, would instantly disintegrate under these conditions. The core uncertainty is so great that NASA's Juno mission was sent in 2016 precisely to measure its gravitational field and try inferring internal structure. Data indicate the core may be diffuse, that is, not a solid block, but a wide region composed of rocks and ice mixed with metallic hydrogen. This scenario is different from anything we know and raises questions about the planet's own formation. If it were possible to see Jupiter's core, there would be no firm ground, but an incandescent and turbulent mass, mixing heavy materials dissolved in metallic liquids. It would be like looking at a star's heart that never managed to ignite. This comparison isn't exaggerated. Jupiter has composition similar to the Sun's and could have become a star if it were several dozen times more massive. This detail makes the journey even more impressive. Exploring Jupiter's core would be, in a sense, exploring an almost star. Each layer crossed would reveal processes reminiscent of stellar physics: incomplete fusion, intense convection, extreme magnetism. Another point to consider is that the boundary between core and atmosphere may not exist clearly. Unlike Earth, where there are well-defined crust, mantle, and core, on Jupiter, everything seems to gradually dissolve. This means even reaching the end of the journey, we wouldn't find a fixed point. It would be more like crossing increasingly dense layers until the distinction between atmosphere and core ceased making sense. Gravity in this region would also be crushing. On Jupiter's visible surface, gravity is already 2.5 times Earth's. In the interior, it grows colossally, pulling everything inward. This compression is responsible for keeping hydrogen in exotic states and ensuring the planet's enormous internal energy. It's literally Jupiter's own weight that creates its infernal conditions. Shock waves inside the planet would be another obstacle. Convection processes, compression, and energy release would create intense vibrations like earthquakes on planetary scale. Each mass displacement could release more energy than all Earth's earthquakes combined. With this, if we could really travel to Jupiter's center, the experience would have no return. Pressure would crush any ship long before reaching the core, and temperature would evaporate any material. The most we could achieve would be sending instruments that transmitted beta for a few minutes before disintegrating, as has already happened with probes launched into its atmosphere. No material known by humans, however, would be capable of resisting such conditions. Our probes can only observe indirectly, measuring gravitational and magnetic fields or capturing radio waves. That's why Jupiter's core is an enigma we can only reconstruct with mathematical models and distant observations. There exists a supergiant star so vast it would swallow Saturn's orbit. When we think of the Sun, it already seems like a colossus to us. Its diameter is 870,000 miles, and its volume could house more than 1,000,000 Earths. It's hard to imagine anything bigger, but the universe doesn't settle for repeating modest patterns. There exist stars so gigantic they would make our Sun look like a grain of sand next to a mountain. Some of these supergiants could expand until swallowing Saturn's orbit, placing within themselves all known solar system planets. These stars' size goes beyond imagination. While the Sun is classified as a G-type main sequence star, supergiant stars belong to a rare and ephemeral category. They have dozens of times the Sun's mass, but shine with hundreds of thousands of times more intensity. The consequence of this tremendous brightness is that they burn their nuclear fuel very quickly, living short and intense lives compared to our Sun's calm longevity. An emblematic example is star VY Canis Majoris, located about 3,900 light-years away. In its maximum expansion phase, it's estimated its radius could extend beyond Saturn's orbit. This means if placed at our solar system's center, all planets up to Jupiter and including Saturn would be immersed within its outer atmosphere. A single star would replace space's vastness with a suffocating presence of incandescent plasma. Another notable star is Betelgeuse, the famous red supergiant in Orion constellation. Though smaller than VY Canis Majoris, it's still so immense that if it were in the Sun's place, its radius would surpass Mars's orbit and could approach Jupiter at certain phases. Betelgeuse is visible to the naked eye and gives us a constant reminder that the universe harbors cosmic monsters far beyond our everyday scale. These stars' structure is profoundly different from the Sun's. While our star has relatively stable nuclear fusion layers in its core, supergiants live in permanent imbalance. Their interiors harbor successive element fusions, first hydrogen into helium, then helium into carbon, and so on, until reaching iron. Each layer functions like an onion, with different fusion zones occurring simultaneously, sustaining their immensity against gravity's force. This fight against gravity, however, is unstable. The larger the star, the harder it is to sustain its own weight. Supergiants expand into diffuse atmospheres, so tenuous that even being larger than the solar system, their density is incredibly low. If we could cross VY Canis Majoris's surface, we'd discover there's no sharp boundary, but a gradual transition between space and rarefied plasma composing its outer layers. These layers' temperature also surprises. Despite being stars, many red supergiants have relatively cool surfaces, around 6,300 degrees Fahrenheit, less than the Sun's surface. Extreme heat is concentrated in their cores, but their atmosphere's immensity dilutes energy. This makes them shine in reddish tones, like giant embers floating in space. If the Sun were replaced by one of these stars, Earth would cease existing instantly. It wouldn't just be swallowed, but its matter would dissolve and stellar plasma. Inner planets, Mercury, Venus, Earth, and Mars, would disappear without leaving traces. Jupiter and Saturn would also be within the star, probably slowly dissolving while interacting with stellar material. Only more distant worlds, like Uranus, Neptune, and perhaps Pluto, would remain in orbit, heated by a star that would dominate everything around. A supergiant's gravitational field is equally impressive. Despite its low density compared to the Sun, its colossal mass exerts attraction capable of trapping entire planetary systems. Any nearby object is forced to align with its force, and gas and dust disks around can give rise to new stars or planets. A supergiant is, in many aspects, both a nursery and destroyer. These stars' instability also manifests in colossal eruptions. VY Canis Majoris, for example, has been observed releasing immense amounts of stellar mass into space, equivalent to several Earths in a few years. These mass ejections form complex nebulae around stars, shaped by intense stellar winds. Supergiants' final destiny is as dramatic as their size. When the core accumulates iron, nuclear fusion stops generating enough energy to sustain gravity. Collapse is inevitable. In seconds, the star crumbles upon itself, causing a supernova explosion. Energy released in this event can shine brighter than an entire galaxy for weeks, illuminating distances of thousands of light-years. From the explosion, two possibilities can be born: a neutron star or black hole. The star's mass defines the result. In the case of most massive supergiants, collapse is so extreme that no force can stop gravity, forming a stellar black hole. Thus, these colossi create the universe's most enigmatic objects when they die. Study of these stars is done mainly by telescopes capable of analyzing their light at different wavelengths. Spectroscopy reveals their layers' composition and speeds at which they're expanding. In Betelgeuse's case, recent observations showed sudden dimmings, interpreted as large mass ejections covering part of the surface. These details help astronomers predict when a star might explode in supernova. If a supergiant were close to Earth, its impact would be devastating. Fortunately, none of the known closest supergiants offers this immediate risk. Betelgeuse, despite being in its final phase, is more than 600 light-years away, close enough to be studied, but far enough not to threaten us. While the Sun follows a stable path of billions of years, supergiants are rare and transitory, but their importance is enormous. When exploding, they scatter heavy elements through space, enriching interstellar medium with atoms that will one day form new planets and even life forms. In a way, we can say Earth itself carries supergiants' legacy. The iron in our blood, the calcium in our bones, and the gold in our jewelry were forged in stars of this type, which exploded long before the solar system's birth. In energy terms, comparison is also surprising. While the Sun releases 4.0 times 10 to the 26 watts of energy every second, a supergiant can emit hundreds of thousands of times more. This colossal power makes them shine intensely, even thousands of light-years away, visible in our skies as reddish points, hiding dimensions beyond imagination. Study of these stars also brings clues about the Sun's own future. Although it will never become a supergiant, it will go through a red giant phase in about 5 billion years. At this stage, it will grow enough to swallow Mercury and Venus, perhaps even Earth. The difference is its size will be modest compared to supergiants, which go much further, reaching orbits that include Jupiter and Saturn. The universe may not be infinite, but rather curved upon itself like a sphere's surface. When we look at the sky on a dark night, the sensation is of infinitude. Stars seem to extend forever in all directions without visible boundaries. It's natural to imagine the universe is unlimited, expanding without end. But modern physics invites us to consider another possibility. The universe may not be infinite, but have a finite form without edges, curving upon itself, like a sphere's surface. This idea, simultaneously strange and elegant, redefines our notion of space. The concept comes from general relativity, proposed by Albert Einstein in 1915. According to this theory, gravity isn't a force in the classical sense, but a space-time curvature caused by mass and energy. If stars and planets can deform space around them, why not think of the entire universe as a curved structure? This is the essence of the hypothesis of a finite but unlimited cosmos, where traveling in a straight line would eventually bring us back to the starting point. To understand the idea, analogies are useful. Imagine Earth's surface. It's finite, about 25,000 miles in circumference, but has no edges. If you walk always in the same direction, you'll eventually make a complete turn and return to the initial point. The proposal is that the three-dimensional universe is something similar, but in a higher dimension. Not an endless plane, but a structure closed in itself, impossible to escape because there's no outside. Mathematics describes this through so-called spatial curvature. If the universe's matter and energy density exceeds a certain critical value, space curves positively, like a sphere's surface. In this case, cosmic expansion, initiated in the Big Bang, could one day reverse, leading to a final collapse known as Big Crunch. If density is exactly critical, the universe would be flat, and if lower, it would be open, negatively curved, like a saddle. Modern observations, made by space telescopes like WMAP and Planck, indicate the universe is almost perfectly flat, but with an error margin small enough that the curvature hypothesis is still considered. This means that although current data suggests an infinite cosmos, we can't totally rule out the possibility it's finite and closed. What's lacking is sufficient precision to distinguish between almost flat and slightly curved. This notion of curved universe also connects to cosmic expansion. Since Edwin Hubble's discovery, we know galaxies move away from each other, as if space between them were stretching. This doesn't contradict the curvature idea. On the contrary, in a closed universe, expansion would be just a temporary phase, and space would eventually contract again. The accelerated expansion we observe today, caused by dark energy, still raises doubts about what the final destiny will be. A universe curved in itself would have fascinating implications for our cosmic perception. For example, light traveling for billions of years could, in theory, make complete turns in space and return from another direction. This would mean that in sufficiently deep observations, we could see repeated images of the same galaxies, coming from different trajectories. So far, we haven't identified clear patterns confirming this, but the possibility remains open. Curvature also alters the distance concept. In flat space, the shortest line between 2 points is straight. In positively curved space, like a sphere's, the shortest line is an arc. This means traveling great distances in the universe wouldn't be like following a straight corridor, but like making turns on an invisible surface. What seems linear to our limited perception would be, on cosmic scale, part of a larger curve. Another intriguing point is time's own destiny. If space is closed, time might also have a kind of circularity. The Big Bang would be the beginning of expansion that, at some point, would revert to collapse. And this cycle could repeat in a sequence of universes being born and dying. This hypothesis, called cyclical model, has been studied as alternative to the idea of a unique and linear cosmos. Beyond the sphere analogy, other useful representations exist. One is hyperspace, or fourth spatial dimension. Just as a sphere's surface only makes sense in 3 dimensions, the closed universe can only be fully understood if we imagine it inserted in one more dimension. It's not that this extra dimension exists for us in an accessible way, but rather that it helps visualize how space could curve upon itself without needing edges. The particle horizon, which marks the maximum distance we can observe, also enters this discussion. We see only a fraction of the universe because light needs time to reach us. If the cosmos is truly curved, much of what's beyond our horizon may have already made turns in space, but can never be seen directly. It's like living in a hall of mirrors, where part of the images are distorted and unreachable reflections. From cosmology's standpoint, the curved universe idea isn't just speculative. It directly influences calculations of age, size, and universe destiny. If closed, the cosmos would have limited volume, and its expansion would end in a future of contraction. If flat or open, it will expand forever. The difference isn't just in abstract concepts, but in the very story we tell about everything's origin and end. Galaxies we observe today also serve as clues. The cosmic background radiation pattern, that remaining glow from the Big Bang, shows small temperature variations reflecting space geometry. Studies suggest the universe is flat on large scales, but doubt remains whether small local curvatures could alter this result. Each new measurement is a step in attempting to resolve this millennial question. Is the cosmos infinite or not. From a philosophical standpoint, the curved universe idea resolves a common difficulty. If space were infinite, we'd be surrounded by infinite stars in all directions, and the night sky should be as bright as day. This paradox, known as Olber's paradox, finds solution in a universe that has limits and is expanding. Curvature would be, in this context, a natural mechanism to avoid a blindingly luminous cosmos. If we think about space travel, the curvature notion adds a twist. Going always forward in theory could lead back to the initial point, just like a trip around the world brings us back to the same continent. But the scale is so immense that even at light speed, it would be impossible to complete the journey in a civilization's lifetime. The closed space idea also suggests there's no outside the universe. Questions like what's beyond lose meaning because the cosmos would be everything that exists. Just like there's no north beyond the North Pole, there would be no outside beyond universe edges. This challenges our intuition, but fits relativity logic. Space and time are entities shaped by matter itself, not empty containers. Despite comprehension difficulty, the curved universe idea isn't so strange when we realize we live on a spherical planet. For centuries, humanity believed Earth was flat, until observations showed otherwise. Perhaps in the future, an equivalent discovery will reveal that space also isn't flat and infinite, but rather closed and finite. This scenario would change even how we think about the cosmos's ultimate destiny. An infinite universe could expand forever, becoming increasingly cold and empty. A curved universe could, in theory, collapse back in an eternal cycle of births and deaths. The difference between the two destinies is also a difference between two completely distinct cosmic stories.